Somewhere in the ancient universe, a black hole grew so monstrous its shadow could swallow our entire solar system, then kept feeding. We can't see it, we only see what it does. Light bent into arcs, time dragged to a crawl, galaxies pinned in orbit around pure darkness. So how big can a black hole truly get? And what do TON 618, Phoenix 8 and Holmberg 15A's central monster reveal about how the cosmos builds its largest structures? In the cosmos, there are numbers so large they stop feeling like math and start feeling like weather. Somewhere beyond our instincts, gravity keeps accounts with a precision that can rewrite a galaxy's fate. Tonight, the camera doesn't chase a monster's face. It follows the bookkeeping of mass, the geometry of horizons, and the collateral damage of growth. Because for black holes, big is not one idea. It's a set of scales that disagree unless you ask the right question. There is mass, the true currency, measured in suns, yet it hides behind distance, glare, and our own instruments. There is the event horizon, a boundary drawn in space-time where escape becomes meaninglessly impossible, even for light. And there is the sphere of influence, the region where a black hole's gravity stops being a rumour and becomes the law. To measure any of it, we must work backward from consequences. We read the speed of gas from broadened spectral lines, then infer how deep a gravitational well must be. We time flickers and echoes across an accretion disk, using light itself as a ruler in a place where rulers fail. We map the motions of stars in crowded galactic cores, then fit their orbits to invisible mass, carefully because models can lie. Even the brightest evidence can be treacherous, since orientation, winds, and cosmic dust can imitate the signature of enormity, and yet the giants keep appearing, each one with a different alibi. TON 6018 arrives as a quasar from the early universe, a point of light whose spectrum carries the strain of extreme gravity. Phoenix AA sits at the heart of a galaxy cluster, where hot gas should cool, fall inward, and feed a central engine, unless feedback interrupts the meal. Holmberg 15A offers a quieter scene, an immense elliptical galaxy with a hollowed core that hints at ancient mergers and the slow violence of black hole binaries. These are not simply 3 entries on a leaderboard. They are 3 different contracts with reality, 3 ways we attempt to weigh what cannot be seen, and 3 environments that can either starve a black hole or deliver it a kingdom. In one case, we trust the physics of luminous gas at relativistic speeds. In another, we trust the thermodynamics of cluster plasma and the scars left by jets. In the third, we trust stellar dynamics and the subtle absence of starlight where it should have been, if nothing extraordinary lived there. As we move from chapter to chapter, the mystery sharpens. If a black hole's mass sets every scale, then what sets the mass? Fuel supply, time, spin, or the limits imposed by its own radiation? How do you build something tens of billions of times heavier than the sun without blowing away the very gas you need? And when we claim a record holder, how much of that claim is nature, and how much is the edge of our measurement methods? The answers will not come as a single number on a screen. They will come as a trail of evidence across wavelengths, across epochs, across increasingly unforgiving assumptions, each step closer to the largest black holes, forcing us to redefine what largest even means. This is a journey into extremes, but it is also a forensic story. Every time we say mass, we're really describing a negotiation between gravity and its surroundings, between what falls in, what is driven out, and what survives long enough to be counted. So we begin where certainty is hardest, with definitions, with instruments, and with the uncomfortable fact that the universe does not label its giants for us. We will have to earn each measurement, and in doing so, we will learn why these dark objects may be the clearest archives of cosmic construction. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We'll start by defining what size means for an object you cannot see. Then follow 3 extreme candidates through the evidence that makes them plausible. Along the way, we'll confront the limits of growth, fuel, feedback, spin, and time, before returning to what the biggest black holes truly reveal. A black hole can be bigger than the solar system, yet leave no surface to photograph. We call it an object, but it is really a boundary, an edge written into space-time rather than carved into rock. The event horizon marks where space-time tips inward, and escape becomes impossible even for light. In visuals, it is almost unfair. No texture, no silhouette, no convenient outline. Instead, there is a darkness that is not a colour, but an absence of return. Around it, stars and gas can glow like sparks in a wind tunnel, and that glow becomes our only handle. Start with a scale that sounds like fiction, then treat it like engineering. Take the sun and compress its mass into a point, ignoring the physics of collapse for a moment. Its Schwarzschild radius would be about 3 kilometers, a tiny sphere for a star. That number is not decorative. It is the distance at which the escape velocity equals the speed of light. Now multiply that mass by 1 billion, and the radius stretches past the orbit of Earth. Multiply again, and the horizon reaches toward Jupiter, Saturn, and beyond. The mind tries to picture a ball, but the correct image is stranger, a region where every future-directed path points inward. This is the first twist in the story. For a black hole, size is not a solid edge or a visible crust. Size is a distance, defined by gravity and by light's last chance to leave. The horizon is not a material surface, yet it behaves like one in our accounting. Cross it, and the outside universe loses contact. We need careful language, because black holes offer several kinds of bigness. There is mass, the amount of matter and energy locked into the hole. There is horizon scale, the radius of the event horizon in spacetime. There is gravitational influence, the region where the hole dominates the motions of stars and gas. And there are observable signatures, the light produced by matter falling in. Even the word radius hides a subtlety. In everyday life, a radius belongs to a sphere sitting in space. Here, the radius is defined by the geometry itself, by what spacetime allows light and matter to do. In that sense, a black hole's size is a rule, not a rind. Mass is the headline number, measured in solar masses. 1 solar mass is the sun's mass, a convenient unit for cosmic accounting. Stellar black holes weigh a few to a few dozen solar masses, born from massive stars that ran out of nuclear fuel. Supermassive black holes begin around 1 million solar masses and climb upward. The giants in this film push into the tens of billions, and they force us to ask how growth can be so fast. The basic scale length begins with the gravitational radius. It is written Art equals gm over c squared. It sets the natural unit for distances near a black hole, the way meters set scale in a laboratory. Double it, and you get the Schwarzschild radius Rs equals 2gm over c squared. For a non-spinning black hole, Rs is the event horizon radius. These formulas look simple, and that simplicity is deceptive. They imply that if you know the mass, you know the horizon size. They also imply that the horizon grows linearly with mass, even as density falls. A larger black hole can be less dense on average than water, yet still be more lethal, because tidal forces near the horizon can be gentler, while the point of no return is vastly larger. When we compare horizons to the solar system, we are comparing distances, not objects. The Earth's orbit is 1 astronomical unit, about 150 million kilometers. Jupiter's orbit is about 5 astronomical units. Neptune sits around 30, a faint bead of ice and rock in a wide, cold circle. A horizon measured in astronomical units would swallow the paths of planets, not by touching them, but by replacing the geometry they move through. It helps to imagine a clean, minimalist graphic. A thin ring marks Earth's orbit, then Jupiter's, then Saturn's, and the black hole's horizon expands like a shadowed boundary crossing those rings. Nothing hits the horizon in the picture, yet the meaning is absolute. Inside that ring, outward routes are erased. Another measure matters for galaxies, not for planets. The sphere of influence is the region where the black hole's gravity dominates stellar motions. It depends on mass, and on the random speeds of stars in the host galaxy. In practice, it is where the black hole's pull rises above the background of the galaxy's own gravity. If we can resolve that region, we can weigh the black hole through dynamics. That region is also where the galaxy's central story becomes legible. Stars there are not just orbiting a bright nucleus, they are responding to an invisible central mass. Their velocities, dispersions, and orbital shapes become a kind of seismology, and the black hole is the hidden source. But even that is not the whole story, because black holes can spin. Real astrophysical black holes are described by the Kerr solution, not the simple Schwarzschild case. Spin changes the horizon radius, shrinking it for a given mass. Spin also reshapes the space around the hole, dragging it like a whirlpool, an effect called frame dragging, where space-time itself is pulled into rotation. Historically, this was one of the great reveals of 20th century physics. Einstein's general relativity replaced gravity as a force with gravity as geometry, and Kerr's rotating solution showed that geometry could twist. The math predicted consequences that sound like science fiction, yet the sky keeps offering confirmations. Spin matters because it changes how close matter can orbit safely. The innermost stable circular orbit, the ISCO, marks the last stable path for gas in a disk. For a non-spinning hole, the ISCO sits at 6 reg. For a rapidly spinning hole, it can move inward to near 1 reg for prograde orbits. That shift changes accretion efficiency, the fraction of rest mass turned into radiation. Accretion efficiency is not a detail, it is a lever. A higher efficiency means more light for the same inflow and stronger feedback on the surrounding gas. A lower efficiency means the hole can gain mass more quietly, hiding growth in darkness. When we see a quasar blaze, we are seeing gravity converted into light, and spin helps set the conversion rate. There is a visual logic to it. Gas spirals inward in a brightening disk, heating as it falls deeper into the gravitational well. Closer orbits mean higher speeds, stronger relativistic effects, and more energy released before the gas disappears. The disk becomes a luminous warning sign posted just outside the boundary. So how do we measure something that emits no light and offers no surface? We use indirect lanterns, the glow of matter and the motion of nearby objects. We read the effects, not the thing itself. Every method is a translation from observable data to mass, and every translation carries uncertainty. One lantern is spectroscopy of broad emission lines in quasars. Gas close to the black hole moves at thousands of kilometers per second. Those speeds broaden spectral lines, and the widths encode the gravitational potential. The underlying idea is simple. Faster motion implies a deeper gravitational well, yet the environment is complex, with winds, turbulence, and geometry layered on top. Reverberation mapping provides that size estimate for active galaxies. Variations in the accretion disk's light echo through surrounding gas clouds with a time delay. The delay gives a light travel distance, a physical scale. Combine that scale with line widths, and you get a mass estimate. It is powerful, but it depends on geometry, orientation, and calibration. In a time series plot, the disk brightens first, then a broad line responds like a delayed heartbeat. The lag might be days, weeks, or months, and each lag corresponds to a real distance. Light itself becomes the measuring tape. The method turns variability, which once looked like nuisance, into structure. Another lantern is stellar and gas dynamics in nearby galaxies. We measure how stars orbit in the central region, and we model the gravitational field required. With enough resolution, we can separate the black hole's influence from the galaxy's stars. Gas disks can also trace the potential, but gas can be turbulent and pushed by radiation or jets. This is where telescopes become not just light collectors, but precision instruments. Adaptive optics can sharpen ground-based views, and space telescopes avoid atmospheric blur entirely. Still, the sphere of influence can be tiny on the sky, and a small error in distance or velocity can tilt the inferred mass. Gravitational lensing can also hint at mass, though rarely for a single black hole directly. Massive galaxies and clusters bend light, and central black holes can subtly affect the inner lensing structure. In special cases, lensing and dynamics together can tighten constraints. More often, lensing reminds us that gravity reveals itself through geometry. In imagery, lensing looks like a cosmic mirage. Background galaxies stretch into arcs, and faint rings appear where alignment is nearly perfect. The black hole's role is usually a whisper inside a louder chorus, but that whisper matters when we push to extremes. X-ray and ultraviolet signatures from accretion disks add another layer. The inner disk temperature, the shape of the continuum, and the reflection features can constrain spin and inner radius. Iron K alpha lines can be broadened by relativity, encoding how close the disk approaches the hole. These measurements are model-dependent, but they connect the horizon scale to observable light. Relativity is not just a correction here, it is the signal. Doppler shifts brighten the approaching side of the disk. Gravitational redshift dims and reddens photons climbing out, and light bending warps the apparent shape. The spectrum becomes a fingerprint of extreme gravity, pressed into X-rays. No single method is perfect, and the biggest black holes are often the hardest to measure. At great distances, we cannot resolve the sphere of influence. In bright quasars, the host galaxy is drowned out by the nucleus. In cluster cores, gas is multi-phase and stirred by feedback. The result is a landscape of estimates with error bars and occasional disagreement. Those disagreements are not failure, they are the plot. When two methods disagree, we learn what assumptions matter. When a mass estimate shifts, we learn what data were missing. The largest black holes sit at the edge of our instruments, and that edge is where mystery survives. Now we introduce the three giants that anchor this story. They live in different environments, and that difference may be the clue. One is a quasar in the early universe, shining across billions of years. One sits in a galaxy cluster core tied to cooling gas and violent feedback. One lies in a giant elliptical galaxy, where mergers and stellar history may have built an extreme central mass. TON 618 is the early universe headline. It is an ultraluminous quasar, meaning we see the accretion flow rather than the hole itself. Its inferred mass reaches into the tens of billions of solar masses, depending on method and calibration. If that mass is real, it implies rapid growth when the universe was young. It raises the question of seeds, accretion rates, and whether black holes can grow near the Eddington limit for long periods. The Eddington limit is a balancing act between gravity pulling in and radiation pushing out. If a quasar shines too intensely, its own light can shove inflowing gas away. So TON 618 forces a pointed question. Did it start from an unusually massive seed, or did it find a way to feed efficiently despite that pressure? Phoenix A star is a different kind of monster. It sits at the center of the Phoenix cluster, where hot intracluster gas should cool and form stars. Observations show extreme cooling and extreme feedback in the same system. The central black hole is implicated as the engine that heats and regulates the core. Its mass is less certain than its influence, but it represents a pathway where environment and fuel supply are extraordinary. In a cluster core, the visuals are layered. X-ray maps show a glowing atmosphere of hot plasma, while optical images reveal filaments and bursts of star formation. Jets can inflate cavities like bubbles in a boiling pot, and the black hole sits at the center of that turbulence, small in size, enormous in consequence. Holmberg 15A offers a third pathway, quieter but potentially enormous. It is a giant CD galaxy near the center of a cluster with a vast stellar envelope. Claims have placed its central black hole in the ultramassive category, perhaps tens of billions of solar masses. The evidence comes from galaxy core structure and stellar dynamics, and the debate remains active. If confirmed, it would connect the largest black holes to the history of repeated mergers. Its core is part of the intrigue. Some giant ellipticals show scoured centers, where stars are missing compared to a simple profile. One interpretation is that past black hole binaries flung stars outward as they hardened, leaving a depleted core as a fossil signature. These three names are not just a list, they are a test of ideas. If TON 618 is truly that massive so early, growth must be efficient or seeded large. If Phoenix A star is fed by a cooling flow, clusters may build giants through sustained fuel delivery. If Holmberg 15A hosts an ultramassive hole, mergers and core scouring may be the signature of extreme assembly. To compare them, we must keep our definitions straight. Mass tells us how much gravity is present. IAC and RG tell us the horizon scale and the natural unit of distance. The sphere of influence tells us where the black hole shapes stellar motions. Spin and ISCO tell us how the accretion engine converts infall into light. We also need to keep our humility. A quoted mass is not a fact carved in stone, it is a model constrained by data. Broadline masses depend on calibration samples and orientation. Dynamical masses depend on resolving power and assumptions about stellar orbits. Cluster core estimates depend on disentangling gas physics from gravity. The largest black holes are where systematic errors can masquerade as discovery. And yet, uncertainty does not weaken the story, it sharpens it. If the universe can build objects this extreme, then our models of feeding, feedback and assembly must be equally robust. Each tension in the data is a chance to learn which physical process is doing the heavy lifting. Yet the stakes are real, because these objects sit at the intersection of cosmic history. Supermassive black holes correlate with galaxy bulges, suggesting coevolution. Jets and radiation can heat gas, quench star formation, and shape cluster cores. The biggest black holes may be fossils of the most extreme growth episodes, preserved in the centers of the largest structures. So the central question becomes sharper. How big can black holes truly get, and what mechanisms build them? Are the giants rare accidents, or inevitable outcomes of hierarchical structure formation? Do they grow mostly by swallowing gas, by merging with other black holes, or by both in different eras? We began with a horizon that could swallow planetary orbits, and we end with a measurement problem. We cannot see the boundary, but we can map its consequences. We can weigh the invisible by watching light broaden, echo, and bend. We can infer spin by reading the inner disk's relativistic fingerprints. Next, we follow the food. We move from definitions to supply lines, from radii to rates. We ask what fuels a black hole, what limits its appetite, and why the largest ones may record the universe's most violent growth spurts. Chapter 1 gave us a ruler for the dark, a way to weigh what cannot be seen. Chapter 2 asks how the ruler's numbers become real objects, how mass actually accumulates, and why growth leaves such bright fingerprints. A black hole grows by eating, but the meal is almost never swallowed whole. Gas arrives with angular momentum, meaning it carries sideways motion as well as inward pull. Even when gravity dominates, that sideways motion acts like a barrier, so the gas cannot simply drop straight in. Instead, it circles, collides, and gradually settles into a disk, flattening like water in a spinning bowl. In visuals, the disk is a luminous vinyl record around a black center, with brighter inner rings and cooler outer bands. The disk is not just scenery, it is a machine that turns orbital energy into heat. That heating is not mysterious once you name the energy source. Gas in orbit has enormous kinetic energy, and as it moves inward it must shed energy and angular momentum. The disk converts the difference in gravitational potential into thermal motion, and thermal motion becomes light. To move inward, gas must lose angular momentum, because angular momentum is what keeps it circling. In a perfectly smooth disk with no friction, each ring would orbit forever, locked in place. Yet real disks evolve, meaning they find an effective friction even when the gas is thin. The key is that viscosity in accretion theory rarely means ordinary stickiness. In astrophysical plasmas, microscopic collisions are too rare to do the job quickly. The disk instead builds a collective turbulent viscosity, an emergent drag created by chaotic motions and magnetic stresses. Turbulence and magnetic fields create viscosity in practice, and the mechanism has a name that changed the field. The magnetorotational instability, or MRI, arises because disks rotate differentially. Inner rings orbit faster than outer rings. A weak magnetic field links neighbouring rings like elastic bands, and that coupling transfers angular momentum outward. Picture two adjacent rings connected by invisible magnetic threads. The inner ring tries to run ahead, stretching the field and tugging the outer ring forward. The outer ring gains angular momentum and drifts outward, while the inner ring loses angular momentum and sinks inward. Inner gas spirals down. Outer gas drifts up and out. The price of that rearrangement is energy released as radiation, because the inward-moving gas falls deeper into the gravitational well. Accretion is gravity converted into light, and the conversion can be astonishingly efficient. Per unit mass, it can beat nuclear fusion, because the potential well near a black hole is deeper than the binding energy released in stellar cores. Fusion turns about 1% of mass into energy over a star's lifetime, while accretion can radiate several percent to tens of percent quickly. A thin disk around a supermassive black hole can shine like a galaxy, even though the disk itself is smaller than our solar system. The quasar is not the hole, it is the feeding glow, an incandescent announcement that matter is losing energy fast. The disk heats as it falls inward, and temperature becomes a map of radius. Farther out, where the gravitational drop is gentler, it radiates optical and ultraviolet light. Closer in, where orbital speeds approach a significant fraction of light speed, it radiates extreme ultraviolet and X-rays. If we could hover above the disk, the view would resemble a bullseye of colour and intensity. Outer regions would glow bluish-white, while inner regions would flare into harsh, invisible ultraviolet. Near the centre, the disk's light would be so energetic that it ionizes atoms, stripping electrons from nuclei. Above the disk, a hot corona can scatter photons to higher energies. turning softer light into X-rays through inverse Compton scattering. The corona is tenuous and extremely hot, millions to billions of degrees in effective temperature, more like a magnetized fog than a surface. Around the disk, gas clouds reprocess light into broad emission lines, because fast-moving gas near the black hole emits Doppler-broadened spectral features. Those broad lines are a clue to speed and scale. When we see lines smeared into wide profiles, we infer gas moving at thousands of kilometers per second. The width becomes a kind of seismograph for the black hole's gravity, even from billions of light years away. This is why the biggest black holes announce themselves through brightness. The same physics also sets a limit on appetite. At high luminosity, photons push on matter, and that push is not poetic. It is momentum transfer. Light carries momentum equal to its energy divided by the speed of light, and when photons scatter, they impart tiny kicks. In ionized gas, the key coupling is electron scattering, because free electrons present a large effective target. Radiation pressure acts outward on electrons, and electrons tug ions along through electric forces, keeping the plasma quasi-neutral. Gravity pulls the whole plasma inward, but the outward push grows with luminosity. There is a point where the two forces can balance. When outward push balances inward pull, the system hits a ceiling, and the ceiling has a precise definition. That ceiling is the Eddington limit, derived in the early 20th century as astronomers tried to understand why stars and accreting objects do not radiate arbitrarily brightly. The idea is simple in plain language. Too much light can blow the fuel away. The Eddington luminosity scales with mass, because a heavier black hole has stronger gravity to hold on to inflowing gas. A more massive object can shine brighter before its own light chokes inflow. This is why the limit is so useful. It links a measurable brightness to an inferred mass scale. Write it as a proportionality. L-YED is proportional to m, and the constant comes from gravity, light speed, and the electron scattering cross-section. The cross-section is the Thomson value for low-energy photons, and it sets how strongly light couples to electrons in a fully ionized plasma. From luminosity, we define an Eddington accretion rate, which translates a brightness ceiling into a mass flow ceiling. It is the inflow that would produce lead for a chosen radiative efficiency. In other words, it is the amount of matter per second you must feed the disk to reach the Eddington brightness. Efficiency matters because not all in falling mass becomes light, even in a bright quasar. Some energy stays in the flow as heat, magnetic energy, or kinetic motion, and then crosses the horizon. The black hole does not care whether the energy was radiated. It only cares what crosses the boundary. In the standard thin disk picture, efficiency is set by the innermost stable orbit, the last radius where circular motion remains stable. Inside that orbit, gas plunges inward too quickly to radiate much more. The closer the orbit, the more energy can be radiated before the plunge. Spin moves that orbit, and spin is not a decorative parameter. A rapidly spinning black hole drags space-time around with it, an effect called frame dragging. For prograde gas orbiting in the same direction, the innermost stable orbit moves inward, letting the disk radiate more of the available gravitational energy. That raises efficiency and increases luminosity per unit mass, which sounds like a clear advantage. Yet the trade-off is subtle but central, because growth is measured in added mass, not in produced light. Higher efficiency means more light for the same inflow, but it also means less mass added per photon produced. If two quasars shine at the same luminosity, the higher spin system accretes less mass per unit time. Its growth is slower even as it looks brighter, because more of the supplied mass energy is being converted into radiation rather than retained. The same observed glow can therefore hide very different growth histories. This connects back to Chapter 1's warning, and it sharpens it into a rule of thumb. Observed light is not the mass. Light is the conversion rate of gravity into radiation, and that rate depends on spin, geometry, and how efficiently the disk cools. Now add time, because time is where the universe becomes unforgiving. If a black hole accretes at the Eddington rate with fixed efficiency, its mass grows exponentially. Exponential growth is deceptive, because it starts slowly and then accelerates, with each doubling taking the same amount of time. The characteristic timescale is the salpeter time, named after Edwin Salpeter, who helped formalize how luminous accretion translates into growth. It is the E-folding time for Eddington limited growth, meaning the time required for mass to increase by a factor of E, about 2.7. For typical efficiencies near 10%, the Salpeter time is tens of millions of years, often quoted around 40 to 50 million. Each E-fold multiplies mass by about 2.7, and several E-folds stack quickly into enormous factors. In a timeline graphic, the curve rises gently at first, then steepens like a cliff. To grow from a stellar seed to a 10 billion solar mass giant, you need many E-foldings, and you need them without long interruptions. You also need the fuel supply to stay steady, because exponential growth collapses if the engine repeatedly starves. A black hole cannot make up time easily if it spends long periods dim. This is where the early universe becomes a clock, and the clock has a hard start. High redshift quasars appear when the cosmos is less than 1 billion years old, meaning their light left when galaxies were still assembling their first substantial bulges. If their masses are already billions of suns, the arithmetic becomes tight. Seeds must be large, accretion must be sustained, or limits must be bent. That statement is not drama, it is bookkeeping. If you assume ordinary efficiencies and strict Eddington-limited feeding, some observed quasars appear to demand an implausibly perfect diet. The Eddington limit, however, is not a law of nature carved into the horizon. It is a balance derived for spherical symmetry and steady isotropic radiation. Real accretion is not spherical, and real radiation is not always evenly distributed. Disks are flattened, and flattened systems have escape routes. Radiation can escape preferentially along poles, where density is lower, while the disk plane remains comparatively shielded. Geometry alone can loosen the effective grip of radiation pressure on the inflow. One route to faster growth is super-Eddington accretion, where the mass inflow exceeds the Eddington rate. The luminosity may hover near Eddington while the mass inflow exceeds it, because not all produced photons escape. In that regime, the black hole gains mass faster than its brightness suggests. Slim disk models capture this behavior, and they modify the thin disk picture without abandoning it. At high inflow rates, photons are trapped in the flow and advected inward, because diffusion outward is too slow compared with the inward drift. The disk becomes thicker, more pressure-supported, and less able to radiate efficiently. The trapped radiation crosses the horizon instead of pushing gas away, reducing the outward force that would otherwise halt inflow. The system can add mass rapidly without proportionally increasing outward pressure, which is why super-Eddington phases are so tempting in early growth scenarios. Yet the same trapped energy can also drive powerful winds from the disk's surface. Another route is anisotropy, where radiation is not emitted equally in all directions. If radiation is beamed away from the disk plane, through funnel-like structures or polar channels, equatorial inflow can continue even at high apparent luminosity. To a distant observer, the system can look outrageously bright while still feeding efficiently. Outflows still occur, but they may not expel all fuel, especially if the surrounding galaxy is deep enough to retain gas. The question becomes how often nature sustains these conditions and for how long, because brief bursts help only if they recur. A single episode can be dramatic, but monster growth requires repetition or endurance. Super-Eddington phases are invoked because timing is unforgiving, and because early galaxies can be unusually gas-rich. They may be common in brief bursts, especially in dense, compact systems where inflows are driven by violent instabilities. In that era, galaxies are not settled spirals, they are turbulent, clumpy reservoirs. Yet super-Eddington growth cannot be assumed everywhere, because feedback fights back. Radiation, winds, and jets can heat the surrounding medium, and the environment decides whether fuel returns. Growth is therefore not just a property of the black hole, it is a negotiation with its host. To start the growth, the universe needs seeds, the initial black holes that later become supermassive. The smallest plausible seeds come from population 3 stars. The first generation formed from pristine gas with almost no heavy elements. Without metals to cool efficiently, these stars can become very massive, and some end their lives as black holes. These remnants are typically tens of solar masses, perhaps up to a few hundred in favourable cases. Stellar seeds are easy to make in principle, because star formation is widespread. They are hard to grow fast enough without long uninterrupted feeding, and interruptions are common in young galaxies. A second channel is direct collapse, and it is attractive because it jumps the starting line forward. In special halos, gas may avoid fragmenting into stars and collapse into a massive object, sometimes described as a supermassive star or a quasi-star stage. That object can then form a black hole of 10,000 to 1 million solar masses, Such a seed shortens the growth problem immediately because it removes many required E-foldings. Direct collapse requires conditions that are rare but plausible in the early cosmic web. The gas must stay warm enough to resist fragmentation, and molecular hydrogen cooling must be suppressed by radiation backgrounds. Molecular hydrogen is a powerful coolant in primordial gas, and cooling encourages fragmentation into many smaller stars. If ultraviolet radiation dissociates molecular hydrogen, the gas remains hotter, pressure remains higher, and collapse can proceed more coherently. In visuals, we might see a dark halo filling with glowing gas that refuses to break into sparks. A third channel is runaway mergers in dense clusters, where stellar dynamics does the assembling. Massive stars collide, build a very massive star, and then collapse into an intermediate mass black hole. This route depends on extreme densities, because collisions require close packing and short timescales. Cluster seeds can bridge the gap between stellar remnants and direct collapse, offering an intermediate starting mass. Their viability depends on cluster density and early dynamics, including how quickly massive stars sink to the center through mass segregation. The early universe provides many compact clusters, but not all will meet the necessary conditions. Evidence to distinguish seeds is indirect, because we rarely observe the birth itself. We look for the mass distribution of early black holes, the occupation fraction in small galaxies, and signatures of early feedback. If many dwarf galaxies host central black holes that hints at common seeding, while a low occupation fraction hints at rarer channels. Gravitational waves may help because mergers carry a clean mass signature. Mergers of intermediate mass black holes could reveal a population built by clusters or early direct collapse, especially if detected across a range of redshifts. The waveform encodes masses and spins, turning spacetime itself into a measuring tape. Electromagnetic clues may also appear, though they are messier. The faint end of the quasar luminosity function encodes how many black holes were active at early times. If faint quasars are abundant, it suggests many seeds are growing. If they are scarce, growth may be limited to special environments. Seeds alone are not the whole story, because even a large seed must keep eating. It must also survive the violence of galaxy assembly, where gravitational encounters reshape orbits and strip gas. The early universe is not gentle, it is a construction site. Galaxies grow hierarchically, a prediction of cold dark matter cosmology confirmed by simulations and observations. Dark matter halos merge, and gas follows the deepening potential wells, shocking, cooling, and settling into new configurations. Each merger rearranges angular momentum, sometimes feeding the center, sometimes stirring it. When halos merge, their central black holes can meet, but the path to coalescence is not automatic. It is a sequence of dynamical stages, each with its own timescale and potential bottleneck. The story of mergers is therefore also a story of delays. First, dynamical friction drags the black holes toward the merged galaxy's center. They lose orbital energy by stirring stars and dark matter, leaving a wake that tugs backward like gravitational molasses. In imagery, two dark points sink through a sea of starlight, carving subtle ripples in the distribution. Then a bound binary forms, and the dynamics change. The binary hardens by interacting with stars that pass close, flinging them outward and shrinking the orbit. Each ejected star carries away energy and angular momentum, and the galaxy's core can be scoured into a lower density region. This process can stall, because the supply of stars on intersecting orbits is not infinite. The loss cone of intersecting stellar orbits can empty, and the binary can linger at separations of about a parsec. That bottleneck is the final parsec problem, a phrase that captures how a small distance can become a major obstacle. Gas, triaxial galaxy shapes, and repeated mergers can refill the loss cone and keep hardening going. Non-spherical potentials can torque stellar orbits, sending fresh stars into the danger zone. Gas disks can also exchange angular momentum with the binary, providing an additional channel to shrink the orbit. If the binary reaches milliparsec scales, gravitational radiation takes over, and the tone of the story shifts. Then the orbit decays rapidly and the black holes merge, releasing energy in gravitational waves that briefly outshine the universe in that channel. The final moments are silent to our eyes, but loud to spacetime. Mergers add mass in chunks, but they also change spin, sometimes spinning the remnant up, sometimes down. The outcome depends on mass ratios and orientations, and on how spins were aligned before the collision. Spin matters because it feeds back into radiative efficiency, shaping how future accretion looks. Mergers can also eject the remnant through gravitational wave recoil, a kick produced when waves carry away momentum asymmetrically. A strong kick can displace the black hole from the center, affecting later feeding, because the densest gas usually sits at the bottom of the potential well. In extreme cases, a remnant can oscillate through the galaxy or even escape a small halo. In the biggest systems, repeated mergers are expected, especially in cluster environments. Cluster-central galaxies experience many dry mergers that add stars and black holes with little gas. Those events build enormous stellar envelopes and can assemble very massive black holes even when cold gas is scarce. This points toward two growth modes that can coexist across cosmic time. Gas accretion dominates in quasar phases, when disks blaze and radiate efficiently. Mergers dominate in massive ellipticals and cluster cores, where galaxies collide without much cold gas, and black holes combine more than they feed. Both modes are regulated by feedback because growth changes the environment that enables growth. The same accretion that grows the hole can heat and expel the fuel, altering the density and temperature of surrounding gas. Feedback is therefore not a footnote, it is the thermostat. Feedback comes in two broad flavors, and both are visible in different wavelengths. Radiative feedback drives winds from luminous disks, pushing gas outward through radiation pressure and thermal heating. Mechanical feedback launches jets that drill through surrounding gas, guided by magnetic fields and powered by the black hole's spin and accretion flow. Winds can sweep cold gas from galactic centers, quenching star formation and starving the nucleus. Jets can inflate cavities in hot atmospheres and prevent cooling from resupplying the nucleus. In X-ray images of clusters, these cavities appear as dark bubbles carved into glowing gas, negative space that reveals invisible power. Feedback is a limiter, but also a sculptor, because it imprints regularities on galaxies. It links black hole mass to host galaxy properties, suggesting that growth is not random. The M-sigma relation captures this link, showing that more massive black holes live in galaxies with higher stellar velocity dispersion. Velocity dispersion is a measure of how fast stars move in the bulge, and therefore how deep the gravitational potential is. The relation suggests coevolution, though the causal arrow is debated. Either the black hole regulates the bulge, or the bulge regulates the black hole, or both respond to shared assembly and gas supply. In clusters, feedback shapes the intracluster medium on the largest bound scales in the universe. Jets deposit energy, offset cooling, and maintain hot atmospheres over billions of years. Without that heating, gas would cool rapidly and rain onto the central galaxy, producing far more stars than we observe. Yet cooling never fully stops, and that is where the story becomes interesting again. Cold filaments can condense out of hot gas, forming narrow, luminous tendrils that glow in optical emission lines. Those filaments can feed star formation, and sometimes the black hole itself, creating a cycle of precipitation and reheating. This is the paradox at the heart of monster growth, and it is more than a rhetorical flourish. The engine that eats also heats. The more it feeds, the more it threatens its own supply, and the more carefully the environment must deliver fuel without letting feedback slam the door. So environment becomes decisive, especially for the largest black holes. The biggest objects likely live where gas supply is repeatedly renewed, and where gravity keeps fuel bound even when winds and jets push. Deep potential wells act like cosmic bowls, catching what would otherwise escape. That brings us to cosmology, because black holes do not grow in isolation. They grow inside dark matter halos that assemble from the cosmic web, the filamentary network traced by galaxies and gas. The web sets the traffic pattern for baryons, and traffic determines feeding. In the early universe, filaments funnel gas into halos, and the inflow can be cold and fast. Cold streams can penetrate hot atmospheres and deliver fuel to central regions, especially at high redshift when halos are smaller and cooling is efficient. In visuals, we see pale rivers of gas pouring into a bright node. Major mergers can also drive inflows, and they do so by changing angular momentum. Tidal torques remove angular momentum from gas, pushing it inward and triggering starbursts and quasar episodes. The same disturbance that scrambles stellar orbits can send gas toward the center in dense, dusty flows. At the nodes of the cosmic web, halos become groups and clusters, and the scale of assembly changes. The deepest potentials collect the most baryons and the most merger events, building giant galaxies with extended envelopes. If any place can build a 10 billion solar mass black hole, it is the center of a massive, repeatedly fed structure. This connects the central question to large-scale structure, and it makes the mystery feel less isolated. How big can black holes truly get depends on gravity, environment, and time. The universe sets the rules, but it also sets the schedule. Time is the strictest constraint, because it cannot be negotiated with. The universe offers a finite number of Salpeter times between the first stars and the first observed quasars. If growth is Eddington limited with high efficiency, the clock runs out, and if growth is intermittent, the clock runs out faster. So theorists explore combinations, not single magic bullets. Start with heavier seeds, allow brief super-Eddington phases, add merger-driven jumps, reduce efficiency through low-spin or radiatively inefficient flows, which can hide mass growth behind dimmer radiation. Each option has costs that show up in observations. Heavy seeds require rare conditions, and rarity must match the number of observed early quasars. Super-Eddington flows require special geometry and may drive strong outflows, which could disrupt the very inflow they need. Low efficiency can hide growth, but changes spectra and feedback, potentially conflicting with what we see in quasar colors and line features. Mergers can add mass quickly, but they require galaxies to merge and black holes to coalesce without stalling. The puzzle is not only about reaching a mass, but about doing so while matching what we observe. We can now frame the growth problem cleanly, without losing the sense of wonder. To build the largest black holes, you need a seed, a supply line, and a way around self-limiting feedback. Each ingredient is constrained by physics, and each is constrained by cosmic history. Accretion sets the luminous phase and the Eddington pace, translating fuel into brightness and mass. Spin sets the efficiency and the pace for a given brightness, turning the same luminosity into different growth rates. Super-Eddington physics offers a shortcut, but not a free one, because winds and geometry complicate the gain. Mergers add mass and reshape galaxies, but they face dynamical bottlenecks and recoil kicks. Feedback regulates the whole cycle and ties black holes to their hosts, carving cavities, launching winds, and setting scaling relations. Cosmology supplies the stage, delivering gas and collisions at the web's densest nodes. This is the physical foundation beneath every extreme claim, and it is why numbers alone are not enough. When we hear tens of billions of solar masses, we should immediately ask which pathway dominated. Was the growth luminous and efficient, or dim and hidden, or punctuated by mergers? Did the black hole begin as a direct collapse seed, already massive before its first bright phase? Did it spend long periods near Eddington, maintaining a steady, disciplined inflow? Did it hide growth in photon-trapped flows, where mass piles on faster than light can escape? Did it gain mass through repeated mergers in a cluster core, where galaxies collide like slow-moving continents? Did feedback merely regulate, or did it repeatedly shut the system down? These questions are not optional. They are the keys that unlock the mass budget. The answer may differ across our three anchors, and that difference is part of the lesson. TON 618 is a quasar, so accretion physics is the foreground, and the disk's radiative efficiency becomes a central suspect. Phoenix A sits in a cooling, heating cluster engine, so feedback and supply dominate, and the intracluster medium becomes part of the story. Holmberg 15A points toward merger history and core scouring signatures, where the galaxy's structure preserves a memory of past binaries. The same equations apply to all three. The boundary conditions do not, and boundary conditions are where nature hides its creativity. Their environments decide what the equations can achieve, and their histories decide how often the engine was allowed to run. A black hole can only eat what arrives, and what arrives depends on the cosmic web's plumbing. The mystery is therefore not just how bright, but how supplied. One sentence must carry us forward, because the next chapter is a confrontation with the clock. Armed with growth physics, we enter the early universe to meet TON 618, an object that seems too big, too fast. We leave the mechanics of growth and step into the deep past, where distance becomes time. The farther we look, the earlier the universe appears, because light carries history across expanding space. In a sense, every telescope is also a time machine, its mirror collecting photons that began their journey before Earth existed. On screen, the modern sky feels calm, but the data are restless. Pinpoints of light become spectra, and spectra become timelines, because each wavelength arrives stamped with a cosmic story. The night is not merely dark, it is layered, with nearer starlight sitting atop far older signals. Even the background glow between stars has meaning, because it is filled with faint galaxies and the accumulated light of structure. Redshift is the key translation. Expansion stretches wavelengths, shifting spectral lines toward red, and the amount of stretch encodes how long the light has travelled. In the laboratory, atoms and ions emit at fixed energies, so their line patterns act like barcodes that cannot be faked. Those patterns are also physics made visible, quantum transitions that keep their spacing, even after the universe stretches the entire spectrum. When those barcodes slide to longer wavelengths, we can measure the shift precisely. We define redshift, z, by comparing the observed wavelength to the emitted one, and that simple ratio becomes a proxy for cosmic scale factor. In plain terms, a larger z means the universe has expanded more since the light left. It also means the photons have been diluted and cooled by expansion, arriving weaker and redder than when they were born. At modest distances, redshift behaves almost like a speedometer, echoing Hubble's early discovery that galaxies recede in proportion to distance. Historically, that relation transformed cosmology from philosophy into measurement. An expanding universe was no longer an idea, but a plotted line. The story is often told as a single breakthrough, yet it was built from painstaking spectra, photographic plates, and a debate over what nebulae even were. At high redshift, the interpretation deepens, because expansion history depends on matter, radiation, and dark energy. A high redshift quasar is not just far away. It is a message from a younger cosmos, when galaxies were still assembling their first heavy structures. We're seeing an era when gas was denser, mergers were common, and the ultraviolet background was reshaping the intergalactic medium. In that epoch, the first generations of stars had already seeded space with metals, so the gas was no longer pristine, yet it was still far more turbulent than in today's mature galaxies. Visually, imagine the spectrum itself stretched like taffy. Familiar ultraviolet lines born in fierce radiation fields drift into the optical where our instruments can catch them. The shift is not a blur of uncertainty. It is a measured displacement, line by line, across the detector. On the screen, the peaks slide away from their textbook positions, as if the universe has pulled the ruler out from under them. TON 618 enters as a single extreme beacon in that early landscape. It was identified in surveys as a quasar with unusually strong brightness, and later work placed it at high redshift. The name is plain, but the implication is not, because the light output hints at a central engine operating near physical limits. In the taxonomy of sky catalogues, it is one entry among millions, yet its numbers refuse to look ordinary. In the archival imagery, the object looks deceptively ordinary, just another point among thousands, yet the catalogues flag it, because its flux is too high to ignore and its spectral features refuse to match nearby galaxies. That is often how rare objects arrive in astronomy, quietly, through statistics, before they become legends. A human eye sees a dot, but a pipeline sees an outlier, and outliers are where new physics often hides. If the engine is as powerful as the light suggests, the central black hole must be enormous. The reasoning is not mystical, it is bookkeeping, with gravity as the accountant. Accretion converts gravitational potential energy into radiation, and the conversion efficiency sets how much mass must fall inward. The disk is essentially a machine for turning orbital energy into heat, and heat into light, before the gas finally crosses the point of no return. A quasar is an active galactic nucleus seen in its most luminous mode. The black hole itself stays dark, but in falling gas forms an accretion disk that radiates intensely. That radiation can outshine the host galaxy, turning a compact region into a cosmological lighthouse. Historically, quasars were once puzzling radio stars, and only later did their redshifts reveal that they were not small and nearby, but immense and distant. In visual terms, the host becomes a faint halo drowned by a brilliant core. The quasar's glare saturates detectors, and diffraction spikes cut across the frame, as if the instrument itself is straining. What we see is not the black hole, but the violence of matter losing its orbit. Around that glare, the galaxy's starlight is reduced to a whisper, and even that whisper is smeared by distance and dust. The accretion disk is not a single temperature surface. Friction, turbulence, and magnetic stresses heat the gas as it spirals inward, so the inner disk glows hotter and bluer than the outer disk. Above it, a tenuous corona can scatter photons to X-ray energies, adding another diagnostic layer. Magnetic fields, twisted by differential rotation, act like invisible gears, transporting angular momentum outward so matter can fall inward. Quasars matter in this film because they let us weigh black holes at distances where dynamics cannot be resolved. We cannot track individual stars orbiting TON 618 center, because even the best telescopes cannot separate such tiny angles at such enormous distances. We instead read the spectrum, where gas near the black hole leaves broad fingerprints. It is a clever substitution. When orbits are too small to image, their speeds still imprint themselves on light. Those fingerprints appear as emission lines smeared into wide humps. The broadening is not a defect. It is the signal because it encodes velocity. In the same way a siren changes pitch as it passes, orbiting gas shifts line photons through the Doppler effect. The line profile becomes a statistical portrait of countless clouds, each moving at its own speed and angle. The first clue is luminosity. A quasar's brightness sets a scale for how much mass must be falling inward, given an assumed radiative efficiency. It also sets a scale for the Eddington limit, the balance between inward gravity and outward radiation pressure. In practice, we build a bolometric luminosity by stitching together bands, because no single telescope captures the entire energy budget. The Eddington limit is a simple but profound idea. Photons carry momentum, and when they scatter off electrons in ionized gas, they push outward. If the radiation field becomes too intense, that push can counter gravity and choke off the inflow, at least in an idealized spherical picture. The limit depends on fundamental constants, so it feels almost like a law, yet real disks can bend the rules by being messy and asymmetric. If a quasar shines near Eddington, its luminosity roughly tracks black hole mass. If it shines well below Eddington, the black hole could be larger than the light implies, because the engine is underfed. If it shines above Eddington, the light could exaggerate the mass unless the flow traps photons. That ambiguity is why we do not trust brightness alone, even when the brightness is spectacular. TON 618 is extreme even by quasar standards. Its luminosity is so high that it immediately pushes us toward a very massive central engine, unless we invoke unusual geometry or magnification. That is why it became a centerpiece, because it is bright enough to force the mass question. On screen, the quasar's point source holds steady while the surrounding field fades, as if the universe itself is spotlighting it. Brightness, though, is a slippery guide. Quasar emission can be anisotropic, and dust can hide parts of the spectrum while leaving others intact. The challenge is to convert what we observe into what the engine truly emits, an inference layered on top of another inference. Even the host galaxy can add a subtle continuum, and that contamination matters when we use luminosity as a ruler. But brightness alone is not a mass measurement. The core method for distant quasars is the virial black hole mass estimate, built from broad emission lines. The idea is to treat the broadline region as gas bound by the black hole's gravity, moving fast because it lives deep in the potential well. The word virial signals an assumption of equilibrium, meaning the motions are dominated by gravity rather than a one-way blast outward. In that picture, line width becomes a velocity scale. Faster gas produces broader lines through Doppler broadening, and the width can be measured from spectra with careful calibration. Observers quantify it using measures like full width at half maximum, and they correct for instrumental resolution, so the telescope does not masquerade as physics. They also subtract narrow components and ion blends, because the spectrum is crowded, and crowded spectra can deceive. The second ingredient is a size scale for the broadline region, because velocity alone does not give mass. A small region moving fast could match a larger region moving slower, and both would widen a line in similar ways. To break that degeneracy, we need a radius. Without that radius, the line width is like hearing engine noise without knowing how far away the car is. Size is inferred through a scaling relation. In many active galaxies, the broadline region radius correlates with the continuum luminosity, because brighter disks ionize gas farther out. That empirical radius, luminosity relation becomes a ruler for objects too distant for direct mapping. It is one of astronomy's pragmatic compromises, built from nearby monitoring, then carried outward into the deep field. The physical intuition is straightforward. If the central source emits more ionizing photons, the zone where atoms remain ionized expands, and line-emitting clouds can survive at larger distances. The relation is not perfect, but it is anchored by decades of monitoring nearer active galaxies. Those campaigns were slow science, measured in seasons of telescope time, because variability is the clock that makes the ruler work. Combine the two, and you get the basic virial form, mass scales like velocity squared times radius, divided by the gravitational constant. Then a geometry factor is applied, because we do not know the exact shape and orientation of the emitting gas. That factor is a reminder that we are inferring a three-dimensional structure from a one-dimensional spectrum. That geometry factor is not a minor detail. If the broadline region is a flattened disk, face-on views can make velocities look smaller than they are, because most motion is in the plane of the sky. If winds contribute to the line profile, the width may not be purely orbital motion. The line can become a hybrid of rotation, turbulence, and outflow, and hybrids are hard to calibrate cleanly, so the method carries assumptions. The gas must be roughly virialized, meaning gravity dominates its motions on average, even if turbulence and radiation complicate the details. The line must trace the bound region rather than an outflow, and the calibration must hold at high luminosity and high redshift. Each assumption is plausible, yet each becomes more fragile as we push toward the brightest objects. Those conditions may differ in the early universe. Metallicity, gas density, and the intensity of ionizing radiation can change the structure of the line-emitting region. When we apply a local calibration to a distant quasar, we are betting that the underlying physics remains similar enough. The bet is not blind, but it is still a bet, and TON 618 sits where the odds are hardest to check. TON 618's mass estimate lands in the ultramassive regime, often quoted at order tens of billions of solar masses. Different lines and calibrations shift the number, but the category stays the same because every reasonable path through the data points to something extraordinary. Even conservative choices leave it among the most massive candidates known. The phrase "candidate" matters. Astronomy often advances by narrowing candidates into certainties. The uncertainty is part of the story, because the measurement sits at the edge of the scaling relations. The radius, luminosity relation is calibrated with nearer active galaxies, not with the brightest quasars in the early universe. Extrapolation can introduce systematic bias, especially if the relation bends or saturates at extreme luminosity. A small change in slope becomes a large change in mass when you are already at the top end of the chart. There is also the issue of radiation pressure. In very luminous quasars, the force of light can alter the dynamics of line-emitting clouds, pushing them outward or changing their effective orbits. Some models apply corrections that can change inferred masses, depending on how strongly radiation couples to the gas. The complication is subtle. The same photons that reveal the gas can also move it. Orientation adds another layer. If we view the system at a special angle, the observed continuum can be boosted relative to the line widths, shifting the inferred radius and the geometry factor. A small change in assumed inclination can move the mass estimate significantly, because velocity enters the virial formula squared. On screen, a simple tilt of a disk model changes the apparent line width, making the uncertainty feel almost geometric rather than mystical. Reverberation mapping is the cleanest way to measure the broad line region size directly. The continuum from the disk varies, and the emission lines respond after a light travel delay. That lag gives a physical radius without relying on luminosity scaling, turning time into distance. It is one of the rare techniques in astrophysics where the measurement is almost literal, a delay multiplied by c. Reverberation mapping turns variability into a tape measure. You watch the continuum brighten or dim, then you watch the line flux echo the change as if the gas is answering a call. The time delay multiplied by light speed gives the distance to the line-emitting gas. In the visuals, the continuum-like curve rises, and a second curve follows behind it. Close enough to be related, far enough to be informative. For nearby active galaxies, this method anchors the entire virial mass framework. It provides the radii used to calibrate the radius, luminosity relation, and it reveals that different lines come from different radii. High ionization lines often respond faster, implying they live closer to the black hole. The broadline region is not one ring, but a layered atmosphere, with each ion tracing a different depth. That stratification matters for TON 618, because the lines accessible at high redshift are not always the same ones used locally. Observers may rely on ultraviolet lines that are easier to observe after redshifting, yet those lines can be more affected by winds. The choice of line becomes a choice of risk. It also becomes a choice of telescope, because different instruments specialize in different wavelengths and resolutions. For TON 618, reverberation mapping is brutally difficult. The object is distant, so its observed variability is time-dilated by cosmic expansion, stretching intrinsic months into observed years. The required monitoring spans years, sometimes decades, and the signal must be separated from noise and instrumental drift. A long campaign also has to survive the ordinary chaos of astronomy: weather, scheduling, and changing detectors. Even if the lag could be measured, the line response can be complex in extreme quasars. The broad line region may include winds, stratified ionization zones, and anisotropic illumination from a disk that is brighter along some directions. The echo is not always a simple single delay, and the transfer function can be smeared. What should look like a clean call and response can become a chorus, with different regions answering at different times. So we often fall back to single epoch spectra, with all their assumptions. That is not a weakness of effort, it is the reality of measuring the largest black holes at the largest distances. The universe does not offer convenient laboratory conditions, and we must work with the photons we receive. In that sense, TON 618 is not just an object, but a test of how far inference can be pushed. The accretion disk itself offers another route to inference. In the thin disk framework, the disk radiates like a multi-temperature blackbody, with hotter emission from smaller radii. The peak of the spectrum shifts with black hole mass and accretion rate, and that shift can be modelled. The model is idealized, yet it captures a real trend. Bigger black holes, at similar feeding rates, tend to have cooler disks, and this is where TON 618 starts to behave strangely. Because when you apply this logic to a black hole of tens of billions of solar masses, the disk becomes so cold, by black hole standards, that it starts to defy what we expect a quasar to look like. That single detail hides a clue about TON 618 that most people have never heard, and it changes how you should picture this monster entirely. We'll reveal it later in this video. For now, let's follow the physics, because the logic itself is surprisingly simple. For a given accretion rate, a more massive black hole has a cooler disk, because the same gravitational power is spread over a larger area. That pushes the thermal peak toward longer wavelengths, sometimes into the ultraviolet rather than the extreme ultraviolet. For a smaller black hole, the disk is hotter and peaks deeper in the ultraviolet, where absorption becomes a serious obstacle. The obstacle is not just dust in the host, but hydrogen along the line of sight, which can erase the very photons we most want. In practice, we fit models to the spectral energy distribution. We use the ultraviolet and optical continuum shape, and sometimes X-ray constraints on the corona, to infer a plausible mass and accretion rate. The method is model-dependent, but it cross-checks the line-based estimate, and it can flag inconsistencies. A good fit does not prove the mass, yet a bad fit can warn us that something in the assumptions is breaking. Spin complicates the picture, because it changes the innermost stable orbit, and therefore the efficiency of converting mass to light. A rapidly spinning black hole can radiate more per unit accreted mass, meaning the same luminosity could correspond to a lower accretion rate. Inclination complicates it too, because disks are not equally bright from every angle. In visuals, the inner edge of the disk creeps inward with spin, and the brightness rises, making the same engine look deceptively different. TON 618's spectrum is consistent with an enormous accretion engine. The ultraviolet output is intense, and the implied accretion rate is high, suggesting a sustained supply of gas. Yet dust, absorption, and intervening material can distort the continuum, complicating direct disk fitting and forcing careful corrections. Even small reddening can tilt the spectrum, and a tilted spectrum can masquerade as a cooler disk, which then feeds back into the mass inference. Between us and the quasar lies the intergalactic medium, threaded with hydrogen that imprints absorption features. Those features carve the spectrum like notches, and they remind us that the light has crossed a cosmos that was still evolving. Even the empty space is not empty. It is a record of structure along the line of sight. On screen, the continuum looks bitten into, as if the universe has taken samples from the beam, so the mass remains an inference built from multiple imperfect handles. Broad lines provide velocities, luminosity provides a radius proxy and an accretion scale, and disk models provide a consistency check that depends on spin and inclination. Each handle is useful, but none is immune to systematic uncertainty. The art is in combining them without letting any single assumption dominate the conclusion. This is where the film's central question sharpens again. How big can black holes truly get when our measurements rely on light from the feeding process? TON 618 is not a photographed horizon. It is a set of spectral clues that point to an extreme mass, assembled from line widths, continua, and calibrated relations. The question is not only what is the number, but how stable is the ladder we climb to reach it? To make that mass intuitive, we translate it into horizon scale. The Schwarzschild radius scales linearly with mass, about 3 kilometers per solar mass, and that proportionality is one of the simplest results in general relativity. Multiply by tens of billions, and the event horizon radius reaches tens to hundreds of astronomical units. The math is simple, yet the meaning is hard because our minds are trained on planets, not on space-time boundaries. On screen, the comparison becomes a slow zoom outward. A circle labelled Event Horizon expands past Mercury, past Earth's orbit, and toward the realm of the giant planets. The point is not that the black hole is a giant ball. It is that space-time's boundary can be enormous. The camera lingers on familiar orbits, letting the scale land, then keeps going, because the horizon does not care what feels familiar. That means the diameter can rival the scale of planetary orbits. The horizon could span distances comparable to the outer solar system, depending on the final mass estimate and spin. The comparison is about geometry, not about a solid object expanding through space. If spin is high, the horizon shrinks somewhat, yet the overall scale remains startling, and the gravitational influence extends far beyond the horizon itself. This is also where density intuition fails. Average density inside the horizon drops as mass increases, because volume grows faster than mass, and the radius scales linearly with mass. A black hole this massive can have an average density comparable to air, or even lower, while remaining an inescapable gravitational boundary. That is not a loophole in gravity. It is a reminder that inside the horizon is not the same as made of stuff. That statement sounds like a trick, so it helps to linger on it. The horizon is not a surface of matter. It is a surface of no return, defined by escape velocity reaching light speed. The interior can be diffuse in an average sense, yet the curvature near the horizon still dictates the fate of anything crossing it. In plain terms, you do not hit a wall, you cross a threshold and the geometry takes over. So bigness is mass and horizon scale, not compactness in the everyday sense. The most massive black holes are the least dense on average, even as they dominate their surroundings. TON 618 is a reminder that gravity's reach can be enormous without requiring a hard surface. It also hints at why such objects can sit at the centres of galaxies without tearing everything apart at once. Most of their influence is felt through orbits and gas flows, not through direct swallowing. Now the growth problem returns, with numbers attached. If TON 618 is tens of billions of solar masses at high redshift, it had limited cosmic time to assemble. Under Eddington limited growth with typical radiative efficiency, mass grows exponentially with a characteristic salpeter timescale, and that timescale sets the pace. The growth is like compound interest, except the bank is the surrounding galaxy, and the interest rate is set by radiation physics. The salpeter time is derived from balancing luminosity, accretion rate, and radiative efficiency. For an efficiency near 10%, the E-folding time is roughly 40 to 50 million years, meaning the mass multiplies by E in that interval if accretion stays near Eddington. Exponential growth is powerful, but it is also unforgiving. Miss a few E-foldings early, and the deficit echoes forward, because the later growth is built on what you already have. Take a representative salpeter time of roughly 40 to 50 million years for efficiency near 10%. To grow by a factor of 10 requires a few E-foldings, and to grow by a factor of 1 billion requires many. The early universe offers only a limited number of such steps, especially once we account for delays in forming the first seeds. The clock starts not at the Big Bang, but at the moment a seed black hole actually exists and begins feeding. Start with a stellar mass seed, and the arithmetic becomes brutal. You need near-continuous accretion close to Eddington for hundreds of millions of years, with few interruptions and few wasted cycles. Any long famine breaks the schedule, because exponential growth cannot recover lost time easily, and the early universe was not a calm pantry. Gas was clumpy, galaxies were colliding, and feedback was fierce, and famines are not hypothetical. Feedback from the quasar can heat or expel gas, and star formation competes for the same fuel supply. The black hole must be fed, yet its own radiation can sabotage that feeding, an astrophysical paradox that plays out across cosmic history. On screen, we see jets and winds as translucent cones, pushing against inflowing streams, a tug-of-war written in light and plasma. Start with a direct collapse seed, and the schedule relaxes, but not completely. A seed of 10,000 to 1,000,000 solar masses removes several E-foldings, giving the system a head start. Yet reaching tens of billions still demands sustained feeding, and sustained feeding demands a stable supply line through the host galaxy. The host must keep delivering low angular momentum gas to the center, not just once, but repeatedly, despite the quasar's attempts to blow it away. Super Eddington phases offer another escape hatch. If the inflow exceeds the Eddington rate while luminosity stays near the limit due to photon trapping, mass can accumulate faster than the light suggests. But such phases may drive strong winds, and their duty cycle is uncertain, especially in luminous quasars. The physics is subtle. The disk can become thick, radiation can be trapped and advected inward, and the apparent brightness can stop scaling with the true inflow. Mergers can add mass in jumps, but they require a dense merger environment, an efficient black hole coalescence. At very high redshift, galaxies merge frequently, but the final parsec problem and recoil kicks can delay or disrupt coalescence. Mergers help, but they are not a guaranteed solution. Even when galaxies merge, their central black holes must shed orbital energy, and that last step can be the slowest. So TON 618 forces a menu of possibilities. Either the seed was unusually massive, or the accretion was unusually sustained, or the system experienced repeated Super Eddington episodes, or the mass estimate is biased high by systematics in the broadline method, and the true value is less extreme. The mystery is sharpened by the object's brightness, because brightness is both the clue and the complication. That last option must be taken seriously, because extreme objects stress every calibration. The radius-luminosity relation might bend at high luminosity, and the geometry factor might differ if the broadline region structure changes with accretion rate. When we push beyond the data that trained the method, we are testing the method as much as the quasar. A single outlier can either be a new regime of nature, or a warning that the ruler has warped. Orientation could make the lines narrower than the true orbital speed, lowering the inferred mass if corrected. Radiation pressure could broaden or reshape line profiles in ways that mimic higher velocities, depending on which gas dominates the emission. Each effect can move the estimate, and several could act together. The challenge is that these effects can partially cancel, making the final number look stable even when the underlying system is complex. Gravitational lensing is another uncertainty to check, because lensing can boost apparent brightness. If TON 618 were strongly lensed, we could overestimate its luminosity and therefore its inferred radius and mass. But strong lensing often leaves telltale signatures, multiple images, arcs, or distortions that careful imaging can reveal. The absence of obvious splitting does not eliminate lensing entirely, yet it makes the most dramatic magnifications less likely. For many luminous quasars, strong lensing is not favoured because the expected image splitting is not observed. Mild magnification by large-scale structure can still occur, because the cosmic web acts like a weak lens across many lines of sight. Yet it typically does not create the huge boosts needed to explain away the most extreme luminosities. Weak lensing is a gentle bias, not a magic trick, and it rarely rescues the numbers by itself. Lensing remains a caution, not a default explanation. It is a reminder that the universe between us and TON 618 is not passive, and that gravity can manipulate light as well as matter. The same physics that makes black holes powerful also makes the cosmos an optical system. In visuals, the light path bends through invisible potential wells, a diagram that looks simple, yet represents the mass distribution of everything in between. Environmental clues can help constrain the story. Quasars at high redshift tend to live in massive dark matter halos, because fueling a bright quasar requires deep potential wells and abundant gas. They can mark overdense regions that later become groups and clusters, acting like beacons for future structure. In that sense, a quasar is not only a black hole story but a map pin for the cosmic web. So we ask what surrounds TON 618. Is there evidence for a rich host environment, companion galaxies, or a forming protocluster? The answer is incomplete, because the quasar glare makes host detection hard, and the distance makes faint companions difficult to confirm with certainty. Even when a faint smudge appears near the quasar, we must ask if it is a neighbour, a chance alignment, or a foreground interloper. Still, the logic is strong. A quasar this luminous is likely a signpost of a rare, massive node in the cosmic web, where filaments intersect and gas supply is steady. If the halo is massive, it can funnel gas along filaments and retain material against feedback, at least for long enough to grow a giant. The picture is almost architectural. Gravity builds the scaffolding, and gas flows along it like traffic toward a bright city centre. Host galaxy properties matter because they connect the black hole to the larger assembly of structure. A black hole does not grow in a vacuum. It grows in a galaxy that must also build stars, metals, and a central potential deep enough to hold onto fuel. The galaxy and black hole evolve together, even if one is easier to see. That coevolution is hinted at by correlations in the nearby universe, yet TON 618 asks whether those correlations were already forming so early. In imagery, this relationship is difficult to show directly, so we rely on inference. We picture a forming galaxy wrapped in dark matter, with cold streams feeding its centre, while the quasar erupts in bursts of radiation. The question becomes almost biological. How does a system keep eating while it is also burning? And how many such systems existed, unseen, before the universe thinned and calmed? This is why TON 618 feels like a stress test for early cosmic growth. It sits where the universe is young, the clock is tight, and the inferred mass is huge. It forces us to confront whether our growth pathways are sufficient, or whether we are missing common early phases that later become rare. The object is not just big, it is early, and that combination is what makes it unsettling. The tension is not only about one object. If TON 618 is real at this mass, it implies that the universe can build ultramassive black holes quickly under some conditions. That would reshape how we think about seed formation, accretion physics, and the duty cycle of quasar activity. It would also sharpen a deeper question. Are our simulations underfeeding their black holes, or are our observations overestimating their masses? It would also reshape how we interpret the brightest quasars as a population. The high luminosity end would not just be a tale of ordinary growth. It would be evidence for special environments, special feeding geometries, or special initial conditions. Are these objects the winners of a cosmic lottery, or the predictable outcome of rare but repeatable conditions? If the conditions are repeatable, then the early universe may have produced more giants than we currently count, hidden by dust, selection effects, and limited sky coverage. At the same time, we must keep the measurement humility from Chapter 1. TON 618's mass is not a direct weighing of a resolved sphere of influence, the way we can do in nearby galaxies with stellar or gas dynamics. It is a model-based inference from light that has travelled for billions of years across an expanding universe. The photons arrive clean, but the interpretation is layered, and each layer carries its own assumptions. So the chapter holds two truths in tension. The evidence points to an extreme mass, and the method carries systematic uncertainties that are hard to eliminate at high redshift. The mystery is not whether TON 618 is bright. The mystery is what that brightness truly implies about the hidden mass. The most honest narration is not certainty, but disciplined curiosity, numbers with error bars and conclusions with conditions. We can now restate the central question in the language of this object. How big can black holes truly get, when the early universe had so little time to build them? If TON 618 is tens of billions of suns, then bigness is not an end state. It is a historical record of unusually efficient growth. It is also a record of a host galaxy and halo that managed somehow to keep the fuel coming. And if the estimate is inflated, that also teaches us something. It would mean our scaling relations break at the extremes, and our census of the largest black holes needs recalibration. Either way, TON 618 forces the field to tighten its methods, because the stakes are conceptual as well as numerical. The object becomes a mirror held up to our tools, asking whether they remain true at the edge of the observable universe. The quasar also reminds us that the biggest black holes are defined by what they control. They control gas flows, radiation fields, and the growth of their host galaxies, even when we cannot see the horizon itself. Their darkness becomes legible only through the structures that orbit it, and through the light released as matter falls. In the visuals, the black hole is never shown as an object, but as a centre, an organising absence that shapes everything around it. So we end with a pivot. TON 618 is a lone beacon in the early cosmos, and its environment is inferred more than seen, reconstructed from spectra and theory. Next, we move to a nearby system where environment is unavoidable, and where hot gas and feedback can be mapped in detail. The scale will shrink in distance, yet the drama will remain, because the same physics of feeding and resistance plays out close enough to watch. From a quasar that stretches the early universe, we transition to a modern-day furnace at a cluster's heart. Phoenix A waits at the centre of a cooling flow, where feeding and fighting happen in the same breath. From TON 618's early glare, we drop into the present-day universe's biggest bound machines. Galaxy clusters are the largest gravitationally bound structures, built where cosmic web filaments intersect and merge. In wide shots, they read like knots in a faint lattice, threads of galaxies converging, slowing, and finally surrendering to a shared gravity. The scale is almost deceptive, because a single cluster can span several million light-years from edge to edge. Within that volume, thousands of galaxies orbit like sparks caught in a slow, persistent whirlpool. Their mass is mostly dark matter, invisible yet decisive, shaping the orbits of thousands of galaxies like a hidden scaffold. We infer it through motion and lensing. Galaxies move too fast to be held by stars alone, and background light bends as if a transparent mountain were in the way. That bending gravitational lensing can stretch distant galaxies into arcs and smears that trace the cluster's mass map. What we can see, however, is not the dark matter itself, but the luminous aftermath of its pull. Between the galaxies lies the intracluster medium, a reservoir of plasma so hot it shines in X-rays. The ICM holds most of a cluster's ordinary matter, spread across millions of light-years in a vast dilute atmosphere. If you could see it with your eyes, it would not look like clouds, but like an almost perfectly transparent glow. It is thin, magnetized, and turbulent, yet it dominates the energy budget we can observe. If the galaxies are the islands, the ICM is the ocean, so expansive that it defines the climate of the entire system. When we speak of a cluster's weather, we mean eddies, shocks, cold fronts, and pressure waves moving through this hot sea. The ICM is not empty space, even if it would pass through your hand like vacuum. It is ionized gas at tens of millions of degrees, where atoms cannot keep their electrons and matter becomes a plasma. At those temperatures, hydrogen and helium are fully stripped, while heavier elements retain only their innermost electrons. Electrons and ions exchange energy through collisions, but the plasma is so tenuous that a particle can travel far before it meets another. That odd combination, extreme heat and extreme thinness, makes the ICM a laboratory for physics that is hard to reproduce on Earth. It is a place where collective electromagnetic behavior matters as much as simple fluid flow. In that regime, X-ray emission is mostly thermal bremsstrahlung, plus line emission from heavy elements. Bremsstrahlung is literally breaking radiation, produced when electrons are deflected by ions and shed energy as photons. Because it depends on temperature, the spectrum carries a smooth, sloping signature that tells us how hot the plasma is. The heavy element lines from iron and other metals act like thermometers and chemical fingerprints at the same time. Those metals were forged in stars and spread by supernovae, then stirred into the cluster's atmosphere over billions of years. Some of that enrichment came from early star formation, and some came later from galaxies losing gas as they plunged through the ICM. Every X-ray spectrum is therefore a record of both temperature and history. The brightness traces density squared, so the core can outshine the outskirts by orders of magnitude. A small increase in central density becomes a dramatic increase in X-ray glow, as if the cluster has a luminous heart. Pressure supports the gas against gravity, so temperature and density encode the cluster's potential well. When we map X-rays, we are mapping a living atmosphere held in place by dark matter. The contours of brightness are not just pretty shapes. They are the shadow of gravity drawn in hot light. Even subtle asymmetries can matter, because they reveal sloshing motions and past mergers that have not fully settled. Historically, clusters became X-ray objects before we fully understood their internal plumbing. Early X-ray satellites revealed that clusters were filled with hot gas, not merely collections of galaxies in empty space. That discovery reframed what most of the matter meant in a cluster, because the ICM outweighs the stars by a wide margin. It also introduced a puzzle that would haunt astrophysics for decades. If the gas is radiating so efficiently, why has it not cooled away? The cooling flow idea was born from that tension, and later challenged by sharper spectra and better images. The Phoenix cluster is a modern, sharpened version of that old question. The Phoenix cluster stands out because its core behaves like a system caught mid-crisis. It is among the most X-ray luminous clusters known, signaling extreme central density and rapid radiative losses. In images, the center looks like a bright ember embedded in a broader, fainter halo of emission. Around that ember, the glow fades gradually, like heat bleeding into a cold room, and then drops into the dim outskirts. That brightness is not a decorative flourish, because it implies the gas is losing energy at a ferocious rate. The cluster is telling us, in photons, that the core is bleeding heat. Its core cooling time is unusually short, far below a Hubble time, and in places closer to tens of millions of years. Cooling time is a simple ratio, but it carries a sharp implication. If nothing compensates, the gas must change state. In dense regions, radiative losses can outpace any gentle replenishment, and the plasma's pressure support begins to fail. In many cool core clusters, that would imply a massive cooling flow toward the center. Yet most observed clusters do not form stars at the rates naive cooling predicts because heating intervenes. Phoenix breaks that pattern by hosting an unusually intense starburst in its central galaxy. The central galaxy, Phoenix A, forms stars at a rate far above typical brightest cluster galaxies. Brightest cluster galaxies, or BCGs, are often giant ellipticals with old stellar populations and only modest new star formation. Their light is usually dominated by ancient reddish stars, and their growth is often merger-driven rather than gas-fed. In ordinary cool core clusters, residual star formation is modest, often tens of solar masses per year or less. Phoenix's central star formation is hundreds of solar masses per year in many analyses, depending on IMF and dust corrections. That gap is the clue, because it points to cooling that is not being fully shut down. In infrared views, where dust reprocessed starlight dominates, Phoenix A glows like a furnace hidden inside an otherwise ancient city. Dust grains absorb ultraviolet light from young stars and re-radiate it as warm infrared emission. The dust also hides the youngest region's invisible light, so the starburst can look quieter than it truly is. Correcting for that dust is part of why the star formation estimates vary, but the conclusion remains robust. Something is building stars at a rate that should be difficult in a cluster core. That something is the condensation of hot plasma into cold gas. It suggests that some fraction of the hot ICM is actually condensing into cold gas and turning into stars. It also suggests that the usual feedback thermostat is not fully preventing cooling. In the classic picture, a cluster core is a self-regulating engine, with cooling and heating locked in uneasy balance. Phoenix looks less like a thermostat and more like a system overshooting its set point. The mystery is whether this is a brief flare-up or a persistent flaw in regulation. If it is brief, we are watching a rare phase that most clusters pass through quickly. At the center sits the engine we label Phoenix Aeon. The A designation is a convention used for a compact central radio source associated with a galaxy's nucleus. It signals the active nucleus, not a measured horizon, and it is not a unique name across the sky. Sagittarius A is the Milky Way's central black hole, but the asterisk is not reserved for it. In cluster contexts, Phoenix AA refers to the active galactic nucleus in Phoenix A, the brightest cluster galaxy. The label is a pointer, not a promise, and it tells us where the energy is coming from. The naming matters because the physics is similar, but the scale and environment are radically different. Sagittarius A lives in a spiral galaxy with a modest hot halo and a relatively quiet center today. Phoenix A sits at the bottom of a deep cluster potential, surrounded by a hot atmosphere that outweighs the galaxy's stars. The black hole's immediate neighborhood may be small, but its fuel line is connected to a reservoir measured in trillions of solar masses. That difference in plumbing changes what activity can look like. It also changes what counts as evidence, because the most dramatic signatures can be carved into the ICM itself. In a cluster core, The black hole's sphere of influence is tiny compared to the ICM it affects. Stellar orbits feel the black hole strongly only within parsecs to tens of parsecs for even the biggest masses. The ICM extends hundreds of thousands of light years, and its dynamics are set by the cluster potential. Yet the black hole can still dominate the energy flow because accretion converts small mass into enormous mechanical power. This chapter's version of bigness is not horizon diameter, but leverage over a giant atmosphere. The strange reality is that influence can be measured in cavities, not in kilometers. That leverage depends on efficiency, because a black hole is not a star and it does not shine by fusion. Matter falling inward releases gravitational binding energy, and a fraction of that energy emerges as radiation or mechanical outflow. Even a few % of rest mass energy is staggering when the mass supply is continuous. In clusters, the most important output is often not light, but motion, jets that carry energy outward. Those jets can remain narrow over long distances, like drills cutting through fog before they inflate into lobes. The paradox is that a tiny region can set the thermal fate of a volume that dwarfs the galaxy. Estimating the black hole mass in a distant cluster core is rarely a direct dynamical measurement. We usually cannot resolve stellar proper motions or gas disks at the needed angular scales, especially at the cluster's distance. Instead, we use scaling relations tied to the host galaxy's bulge properties, which are easier to measure from integrated light. The M-sigma relation links black hole mass to stellar velocity dispersion, and the ML relation links it to bulge luminosity or stellar mass. These relations work well in the middle range, but the top end is where the uncertainties grow. At the extreme end, a small change in assumed structure can shift the inferred mass by a large factor. For brightest cluster galaxies, these relations are uncertain at the top end, because the galaxies are extended and merger-built. Their stellar envelopes can be enormous, and their central profiles can be altered by repeated black hole mergers. Those mergers can scour out the core, ejecting stars through gravitational slingshots and leaving a flatter central light profile. Some systems may host ultramassive black holes that sit above the standard relations, but the scatter is large. That uncertainty is not just bookkeeping, because it affects how we interpret the energy budget. If the black hole is larger, it can in principle supply more power without extreme accretion rates. Where available, gas dynamics can help, but cluster cores complicate the picture. Ionized gas can be disturbed by jets, shocks, and turbulence, so rotation curves are not always clean. Molecular gas disks can offer better tracers, but they can be warped, clumpy, and influenced by feedback. Stellar dynamics in BCGs is difficult because the light profile is shallow, and the core is often scoured. Even the definition of bulge becomes slippery in a galaxy with an extended halo of accreted stars. So for Phoenix A, mass estimates often remain indirect, bracketed by host scaling and by energetic arguments. Energetic arguments are a different kind of measurement, because they treat the cluster as a calorimeter. If you can estimate how much work the AGN has done on the surrounding gas, you can infer the minimum power it must have delivered. That power, in turn, constrains how much mass must have been accreted, given plausible efficiencies. It is not a clean mass measurement, but it is a physical boundary condition. The key is that feedback power can constrain accretion history even when mass is uncertain. In a sense, the ICM becomes the black hole's ledger, written in heat and motion. To understand Phoenix, we need cooling flows in plain physics terms. Hot plasma irradiates energy, and radiative losses reduce thermal pressure unless heat is replaced. The cooling time is roughly the thermal energy content divided by the radiative loss rate. In dense cores, cooling time can drop below the time needed for the cluster to evolve, so cooling should be effective. When the gas loses energy, it tends to compress, which can increase density and accelerate cooling, a feedback in the wrong direction. This is why the core can behave like a runaway, unless something interrupts the cascade. As gas cools, it can lose pressure support and drift inward under gravity. In the classic cooling flow picture, hundreds to thousands of solar masses per year would flow to the center. That inflow would build enormous reservoirs of cold gas and trigger sustained star formation. It would also feed the central black hole, potentially lighting it up as a quasar. For a time, this was the default expectation, because the X-ray luminosities seemed to demand it. The term cooling flow sounded almost gentle, but the implied mass transport was anything but. But the classic picture failed as a universal description. High-resolution X-ray spectroscopy showed less gas cooling to low temperatures than expected, with missing emission lines that should have been obvious. The missing cooling implied that heating must offset radiative losses in many clusters. The leading heater is the central AGN, which injects mechanical energy through jets. The cluster core becomes a feedback loop where cooling fuels the AGN and the AGN reheats the gas. It is a cosmic compromise. Cooling never fully stops, but catastrophe is usually avoided. That loop can stabilize near a threshold where cooling triggers precipitation, but runaway cooling is prevented. The threshold is often framed in terms of cooling time compared to dynamical time, a ratio that hints at when gas becomes thermally unstable. When conditions cross that line, cold clouds can condense out of the hot phase. Those clouds can form stars, but they can also feed the nucleus. The loop is therefore not a simple on-off switch, but a cycle with delays and overshoots. The ICM responds slowly, and the black hole responds in bursts, so perfect balance is not guaranteed. Phoenix looks like the loop is slipping. The core shows evidence for both strong cooling and strong heating, as if the system is in a transient phase. One interpretation is timing, because feedback is not instantaneous, and the ICM does not respond like a rigid body. Cooling may have surged, delivering cold gas faster than the AGN can respond, and the response is now catching up. Another interpretation is coupling, because energy can be injected but deposited in the wrong place. The question becomes unsettling. What if the engine is working but the heat is missing the wound? The AGN may be powerful, but its energy may not be deposited where cooling is strongest. Jets can drill through the densest gas and dump energy farther out, leaving the inner core underheated. They can also precess, wobble, or change direction over time, spreading energy unevenly. In some frames, you would expect symmetry, but clusters rarely grant it, and their cores carry the scars of past disturbances. Either way, Phoenix forces us to treat feedback as imperfect and time-dependent, not a steady thermostat. The cluster is not a machine with a constant setting, but a living system with memory. AGN feedback in clusters has a measurable signature in X-rays. Jets inflate cavities, bubbles of relativistic plasma that displace the hot gas and appear as depressions in X-ray surface brightness. In the best images, you can see the cavities like faint bites taken out of the glowing core. Around them, the gas can appear brighter, compressed into rims that outline the bubble's edges. Those rims are not merely outlines because they are where pressure and motion leave their imprint. If you track them carefully, you can almost reconstruct the outburst as a sequence of pushes. The energy in a cavity is often approximated by its enthalpy, about 4 times PV for relativistic contents. We estimate P from the surrounding ICM pressure and V from the cavity size, which we infer from the cavity's projected shape. To turn energy into power, we divide by a timescale, often the buoyancy rise time or sound crossing time. This gives a jet power that can be compared to the X-ray cooling luminosity. It is a practical method, but it carries uncertainties that we have to respect. The bubble's true shape may be elongated along our line of sight, and its contents may not be perfectly uniform. Projection effects can hide the true cavity volume, and the age estimate depends on how the bubble rises and deforms. Even so, the broad conclusion is often stable. The mechanical power can be enormous. In many clusters, the cavity power is comparable to or greater than the radiative losses of the core. That is why jets are taken seriously as the dominant heating channel. They are not decorative radio features, but thermodynamic agents. When you see a cavity, you are seeing work done against gravity and pressure, energy turned into structure. Cavities are not the only channel. Jets can drive shocks that heat gas directly, and repeated outbursts can launch sound waves that propagate through the ICM. Shocks appear as sharp edges or subtle brightness jumps, where temperature and density change across a thin front. Sound waves are gentler, like ripples in a pond, but they can still carry significant energy. Over time, that energy can dissipate through viscosity, turbulence, or plasma processes that are still debated. The ICM may look smooth, but its internal friction is a complicated, magnetized kind of friction. Turbulence can mix hot and cooler phases, redistributing energy and altering condensation. Cosmic rays can contribute pressure and heating depending on transport and confinement. Magnetic fields can suppress conduction across field lines, changing how efficiently heat spreads from hot regions to cooler ones. The ICM is a plasma, not a simple fluid, and its microphysics shapes the macroscopic cooling balance. In other words, the cluster's fate depends on physics that happens at scales far smaller than a galaxy. The smallest instabilities can decide whether a cloud survives long enough to fall inward. In many clusters, the inferred jet power roughly matches the cooling losses, suggesting long-term regulation. Phoenix complicates that tidy picture because cooling indicators remain extreme. The cluster's X-ray luminosity is high, and the central Galaxies star formation implies that cold gas is accumulating. If jet power is also high, then the system is doing both at once. That coexistence is the tension, because it implies either a brief overlap during a cycle or a persistent mismatch in where energy lands. It is as if the core is both burning and being doused, and neither process fully wins. It suggests either a brief overlap during a cycle or a fueling route that keeps cold gas reaching the center despite heating. If the AGN heats mostly at larger radii, the inner tens of kiloparsecs can still cool efficiently. If the heating is intermittent, cooling can proceed during quiet intervals and then be partially quenched later. The observations become a snapshot of a moving target. Phoenix may be rare because we are catching it at a special moment, or it may be rare because most cores never reach this level of imbalance. Fueling is where accretion mode matters. Hot Bondi accretion describes spherical inflow from the hot phase, set by gas density and sound speed near the black hole. It is a clean, elegant formula, but it assumes the gas is smooth and that angular momentum is negligible. In cluster cores, Bondi rates from the hot ICM often seem too low to power the strongest jets, unless conditions near the black hole are much denser than we can resolve. That gap pushes us to consider other pathways. It also reminds us that what happens inside a few parsecs can be hidden behind our resolution limits. Cold chaotic accretion offers an alternative. In that picture, cooling produces multi-phase clouds and filaments that rain inward, collide, cancel angular momentum and feed the nucleus efficiently. The word chaotic is not decoration, because the inflow is clumpy, variable, and driven by condensation physics. Instead of a steady spherical drizzle, the nucleus receives bursts and streams. Those streams can be redirected by turbulence and then suddenly align, delivering a pulse of fuel. That variability can naturally produce cycles of strong feedback followed by renewed cooling. Multi-phase gas is the bridge between X-ray cooling and black hole feeding. We observe hot plasma in X-rays, warm ionized gas in optical emission lines, and cold molecular gas in millimeter lines. In many cool core clusters, these phases coexist in filaments that trace where cooling is fastest. Visually, those filaments can look like luminous threads, draped and tangled, as if the core were wrapped in glowing smoke. Some appear to hang like curtains, and others twist like ropes under tension. They are not mere ornaments, because they mark where hot gas has crossed a thermodynamic boundary. The cold gas can form stars, but it can also lose angular momentum and reach the nucleus. In Phoenix, the large star formation rate implies a substantial cold reservoir, and that reservoir is a plausible fuel source for Phoenix A und. The same condensation that builds stars can also build jet power. That dual use is what makes the system so unstable, because the fuel for regulation is produced by the process that regulation is meant to suppress. The core becomes a self-referential engine, feeding on its own byproducts. It invites a difficult question. How do you regulate a process that manufactures its own trigger? This creates a feedback paradox that is central to the film's question. The black hole needs fuel, and cooling provides it, but the black hole's jets are supposed to stop cooling. If Phoenix is cooling strongly, then either the jets are late, misdirected, or insufficiently coupled. If Phoenix has powerful jets, then either they heat the wrong radii, or the cooling is temporarily overwhelming. The system may be caught between states, and the evidence suggests the balance is not gentle. It is a negotiation conducted through shocks, bubbles, and falling clouds. It may be transitioning from a cooling-dominated phase to a heating-dominated phase, or oscillating with a large amplitude. In that oscillation, the cluster core's entropy rises and falls, and the star formation responds with a delay. The black hole's accretion responds too, but not necessarily on the same schedule. There is no guarantee that the maximum jet power coincides with the maximum cooling rate. The mystery is not whether feedback exists, but how its timing and geometry shape the outcome. Phoenix may be showing us the lag, where cause and effect refuse to line up neatly. We can frame Phoenix as environment-driven growth and environment-driven limits. In a cluster core, the black hole sits at the bottom of a deep potential well that collects baryons over cosmic time. The ICM is a long-lived reservoir that can, under the right conditions, deliver fuel repeatedly. That makes cluster centers plausible nurseries for the largest black holes. Yet the same environment also makes feedback consequential, because heating the ICM changes the fate of huge gas masses. A single outburst can alter whether millions of solar masses condense or remain suspended as hot plasma. The black hole's mass may be measured in solar masses, but its influence is measured in the thermal history of a cluster core. When jets inflate cavities, they are not just moving gas aside, they are changing entropy and pressure profiles. When shocks pass through, they can raise temperature and reduce the ability of gas to condense. Over billions of years, repeated outbursts can keep a core from forming too many stars. The black hole becomes a regulator of galaxy evolution, not by gravity alone, but by energy flow. The cluster core becomes a record of that regulation, layered, disturbed, and never fully at rest. Observations reconstruct this hidden engine by combining wavelengths. X-ray images reveal cavities, shocks, and the cooling core structure, including sharp edges that hint at sloshing motions. Optical and infrared data measure star formation, dust, and emission-line filaments that trace warm gas. Radio maps show jets and lobes that mark where mechanical power is going, sometimes aligning with X-ray cavities like a blueprint. Millimeter observations trace molecular gas that can be both star-forming fuel and AGN fuel. When these layers are overlaid, the core looks less like a single object and more like a conversation between phases. Each band is partial, but together they constrain the cycle of cooling, condensation, and reheating. A cavity without radio emission can imply an older bubble, where relativistic electrons have aged. Bright optical filaments without strong star formation can imply gas that is cooling, but not efficiently collapsing into stars. A mismatch between jet direction and filament orientation can hint at changing jet axes over time. The story is assembled like forensic work because no single instrument sees the whole engine. What looks like calm in one band can be violence in another, an absence that is itself a clue. The Phoenix cluster also forces a careful distinction between luminosity and power. The X-ray luminosity is radiative loss from the ICM, not direct evidence of black hole feeding. The AGN's radiative luminosity can be modest even when its mechanical jet power is enormous. In cluster feedback, the dominant output can be kinetic and enthalpy, not light. That matters for bigness, because the black hole can be growing quietly while doing loud work. The most important energy may be carried by particles and fields we cannot see directly. It can regulate the cluster without looking like a quasar. In many galaxies, we associate black hole growth with brilliant accretion disks and intense radiation. In clusters, the growth can be obscured, intermittent, or mechanically dominated. The accretion flow may be radiatively inefficient, converting more energy into jets than into photons. That difference changes what active looks like in the sky. Phoenix AI can be a powerhouse, even if it is not dazzling in visible light. The drama is written into the surrounding gas, not into a bright central point. We can connect this back to Chapter 1's definitions of size. The event horizon scale grows linearly with mass, but it is irrelevant to the cluster's geometry. The sphere of influence is where stellar motions reveal the black hole, but it is still tiny compared to the ICM. The meaningful size here is the radius over which the black hole can change entropy and cooling time. Cavities and shocks show that radius can be hundreds of thousands of light years, a scale that rewrites intuition. The cluster teaches a new metric, not how big the object is, but how far its consequences travel. In clusters, bigness becomes leverage. A small central engine can move the thermal state of a giant atmosphere, and the atmosphere remembers those pushes. Each outburst leaves behind buoyant bubbles, displaced gas, and altered cooling conditions. Over time, the core can be sculpted into a layered structure with temperature gradients and metallicity patterns that record mixing. Metallicity peaks can mark where enriched gas has been lifted and redistributed by rising bubbles. The cluster becomes a palimpsest of past activity, with new outbursts writing over old ones. When we look at Phoenix, we are reading a page mid-sentence. Phoenix therefore becomes a case study in feedback as a growth regulator that can fail partially. If cooling outruns heating, cold gas builds up, star formation surges, and the black hole may gain mass more efficiently. If heating catches up, jets inflate larger cavities, raise core entropy, and suppress condensation. The system's observed state may depend on when we look in that cycle. Phoenix may be rare because the runaway phase is brief, or because the conditions that trigger it are uncommon. Either way, it shows that regulation is not a guarantee but an achievement. Either way, it is a laboratory for the extremes. It asks a pointed question. How close can a cluster core come to the classic cooling flow regime before feedback reasserts control? It also raises a quieter question about measurement. Are we seeing the true long-term average or a transient spike? In astrophysics, snapshots can mislead because timescales are long and cycles are slow. Phoenix tempts us to mistake a moment of imbalance for a permanent state. The deeper question is whether the universe spends most of its time near equilibrium or merely passes through it. Cosmologically, cluster cores are where galaxy formation models are tested hardest. Without AGN feedback, simulations overproduce stars in massive galaxies because cooling is too efficient and gas collapses too readily. With feedback, models can match stellar masses, but they must also reproduce cavity powers, cooling times, and star formation residuals. Phoenix is a stress test because it sits at the edge of regulation. It suggests that even in the modern universe, the cooling flow problem is not fully solved. It also suggests that the most massive environments still contain room for surprise. It also suggests that the densest nodes can still deliver fuel in ways that challenge steady-state assumptions. The cosmic web funnels matter inward, and clusters sit at the ends of those funnels like collection basins. Over time, mergers and infell can disturb the core, stirring turbulence and changing how gas cools. A slight change in density or a shift in jet coupling can tip the balance. Phoenix may therefore be less an anomaly than a reminder of how sensitive the system is. If the core is a balancing act, then the smallest shove can matter. This returns us to the central question in a new form. How big can black holes truly get when environment keeps refilling the fuel reservoir? Phoenix implies that the path to ultramassive mass may run through deep potential wells and multi-phase precipitation. It also implies that the largest black holes may grow during brief windows when feedback is temporarily outpaced. The universe builds giants not only by feeding them early, but by placing them where gas cannot easily escape. In such places, gravity collects the fuel, and time provides repeated chances. Phoenix A is a titan in a storm of hot gas, but it is also a reminder that influence can exceed mass's immediate reach. The black hole's gravity rules a tiny central region, yet its energy output can govern a cluster core for billions of years. That is the documentary's conclusion theme in miniature. Control is a dialogue between gravity, environment, and time. When the dialogue becomes unbalanced, stars ignite, cavities open, and the cluster core changes character. Phoenix is what that imbalance looks like in X-ray light, and it leaves us wondering what the next swing of the cycle will erase or reveal. Now we pivot from a black hole that sculpts a cluster's atmosphere to a galaxy whose core may hide an even heavier, quieter giant. Holmberg 15A waits with a different clue, written not in hot gas but in starlight and a scoured core. We pivot from Phoenix A's loud feedback to a quieter kind of evidence, the kind that hides in starlight rather than X-ray fire. Holmberg 15A sits at a cluster center, massive, smooth, and strangely hollowed, like a stone worn down from the inside. In wide-field images, the galaxy looks almost featureless, a pale oval surrounded by a faint ghostly envelope. The background is crowded with cluster members, yet this central body seems to absorb attention by refusing to sparkle. Yet the longer we stare, the more the center feels wrong, as if something heavy once lived there and left. Holmberg 15A is a brightest cluster galaxy, a BCG assembled through repeated mergers across cosmic time. It is a giant elliptical, dominated by old stars and pressure-supported motion rather than a rotating disk. The stellar light is smooth because the population is old and because violent relaxation has mixed orbits into a statistical calm. Its outer light is diffuse, spreading into the intra-cluster glow where galaxy and cluster begin to blend. In deep exposures that halo looks like breath on glass, barely there, but unmistakably extended when the contrast is stretched. This is the architecture of a central monarch, built not by gentle growth but by accumulation and cannibalism. The camera can linger on the galaxy's surface brightness profile because the profile carries the first clue. That core is not merely faint, it looks scoured, as if the inner starlight has been sanded flat. The inner light profile flattens abruptly, and the usual steep rise toward the center simply is not there. A normal elliptical brightens inward like a slow, steady hill, but this one levels off into a plateau. In a normal elliptical, starlight piles up toward the nucleus, but here the nucleus seems to have been thinned. Astronomers describe this as a depleted core, and the word depleted matters. It implies subtraction rather than absence, a deficit relative to what the outer profile predicts should exist. When we fit the outer galaxy with a smooth model and extrapolate inward, the centre falls short. That missing light corresponds to missing stars, and missing stars demand a mechanism. Even the geometry of the deficit becomes a clue, because the flattening is too broad to blame on dust lanes or a small star-forming hole. In giant ellipticals, large low-density cores often point to past major mergers, especially dry mergers with little cold gas. Dry matters because gas can radiate energy, sink inward, and form new stars that refill a core. Without gas, the merger is mostly gravity and orbits, stellar systems colliding, mixing, and settling without a luminous rebirth. The mergers bring in central black holes that eventually form a bound binary at the new galaxy's centre. This idea is not new, and it grew alongside the realization that most massive galaxies host supermassive black holes. Once that connection was established, cores stopped looking like simple photometric quirks and started looking like dynamical fossils. Core scouring is a gravitational slingshot process, not an explosion, and that distinction keeps the story grounded. As the binary hardens, passing stars steal orbital energy and get ejected outward. The stars are not vaporized, and the galaxy is not blown apart. Instead, the binary acts like a moving gravitational trap, repeatedly flinging stars away and deepening the central deficit. The core becomes a negative image of the binary's past, an imprint made by subtraction rather than addition. Each three-body encounter is small in isolation, yet relentless in aggregate. A star wanders close, feels the changing gravity of two enormous masses, and leaves with a new trajectory. Often it is kicked to a wider orbit within the galaxy, and sometimes it is accelerated enough to escape entirely. Those escapes do not look like fireworks, but they concede a faint population of high-velocity stars drifting through the cluster. The binary shrinks, the core empties, and the central density drops, one interaction at a time. This process has a characteristic rhythm that theorists have studied for decades. At first, dynamical friction brings the two black holes together, as each one plows through stars and dark matter. That drag is not literal friction, but a gravitational wake, an overdensity that tugs backward and drains orbital energy. Then the pair becomes bound, and the hardening begins, driven by repeated stellar encounters. Later still, if the binary becomes tight enough, gravitational waves can take over and complete the merger, though the handoff is not always guaranteed. The so-called final parsec problem, where the stars keep refilling the loss cone, lurks behind every confident timeline. The result is a core whose size can scale with the merger history and the binary's mass, which makes the core feel like a measuring stick. Bigger binaries can excavate bigger deficits in starlight, and repeated mergers can enlarge the damage. Simulations often express the deficit in terms of missing mass, comparing it to the final black hole mass. The ratio is rarely 1-to-1, because each merger can eject several times the black hole mass in stars. Yet nature adds scatter, and the same core size can be produced by different sequences of events. That link tempts an inference that is both powerful and dangerous, because it turns a photometric feature into a mass claim. If the core is enormous, the central black hole might be enormous too. The temptation is understandable, since direct measurements at these scales are rare, but the danger is that the core is a record of interactions, not a single clean imprint. A core can remember multiple mergers, and it can forget details about which merger mattered most. Holmberg 15A became famous because some analyses suggested an ultramassive black hole far beyond the usual supermassive range. The numbers reached into the tens of billions of solar masses, territory normally reserved for the brightest quasars. For a nearby galaxy, such a claim feels almost paradoxical, because nearby should be easier. Yet the nearer we get to the extreme end, the more measurement becomes a battle with subtlety. The galaxy is close enough to map, but not close enough to make the central parsec feel large. If true, it would compete with the giants inferred from quasar light, but with an important difference in method. It would also be nearby enough to test with dynamics rather than relying on luminous accretion signatures. Quasars tell us about black holes that are actively feeding, but Holmberg 15A asks about a black hole that may be massive while nearly silent. That contrast is part of the mystery this chapter is built to hold. It asks a quiet question. Can the universe hide its largest masses inside its calmest galaxies? But this chapter is about how hard nearby still is at the top end, even when the galaxy is not at cosmological distance. Even in the local universe, the biggest masses push measurements to limits set by angular resolution and by the complexity of real galaxies. A cluster center elliptical is not a tidy laboratory object. It is an evolved system with layered histories and overlapping gravitational components. The light looks simple, but the mass can be distributed in ways our eyes do not anticipate. To weigh a quiet black hole, astronomers use stellar dynamics, which is both elegant and unforgiving. They treat the galaxy as a swarm of test particles responding to gravity, each star tracing the potential with its orbit. The black hole's mass is not seen directly, but it shapes the speed distribution of stars near the center. In principle, gravity is honest, and the stars cannot lie. In practice, the stars speak in a blended chorus that we must translate. The observable is not the black hole itself, but the velocities of stars projected along our line of sight. Spectral absorption lines broaden and shift with motion, and the amount of broadening encodes the velocity dispersion. In practice, we are measuring the collective imprint of millions of stars blended into one spectrum, a calcium triplet line, a magnesium feature, a forest of weak absorptions. All of them carry kinematic information if the signal is clean enough. The sharper the spectrum and the better the calibration, the more faithfully we can recover that imprint. We map those line profiles across the galaxy to build a spatially resolved kinematic field, not just a single number. We need high signal-to-noise spectroscopy, stable instruments, and careful subtraction of sky background. Integral field units can turn the galaxy into a grid of spectra, letting us watch dispersion change from pixel to pixel. The cluster environment complicates this, because diffuse intracluster light can contaminate the outer regions. Even the choice of spectral templates can matter, since different stellar types imprint different absorption features. A mismatch can masquerade as extra broadening, quietly biasing the inferred dispersion. The goal is a velocity dispersion profile and, when possible, higher moments that capture asymmetry in the line-of-sight velocity distribution. Those details help separate rotation, random motion, and anisotropy, which all contribute to the observed line shapes. A simple Gaussian width is rarely enough for giant ellipticals. Subtle wings and skewness can carry crucial information about orbit families. In a depleted core, those wings can be faint, which makes the measurement feel like listening for a whisper in a cavern. Then comes the modelling step, where the real uncertainty often hides behind technical competence. The standard tool is orbit superposition, often called Schwarzschild modelling, after Martin Schwarzschild's pioneering work. The method was developed to handle galaxies that are not simple analytic systems. It is powerful because it can represent complex orbit structures, but it is also flexible enough to fit the data in more than one way. That flexibility is a strength, and it is also a warning label. In Schwarzschild models, we assume a gravitational potential and populate it with many possible stellar orbits. We then weight those orbits to match the observed light distribution and the kinematics across the field. The orbits can be radial, circular, boxy, or tube-like, depending on the assumed symmetry. If the galaxy is mildly triaxial, box orbits can dominate the center and complicate interpretation. The final model is a carefully tuned mixture that reproduces what the telescope sees. It is a reconstruction of an invisible architecture from visible motions. The potential includes stars, dark matter, and a central black hole, and each component has parameters that can slide. The black hole mass is adjusted until the model best reproduces the data, but best depends on the adopted priors and the error model. The stellar mass is tied to the light through a mass-to-light ratio, and the dark halo is described by a profile with its own scale and concentration. When the data are limited, these components can trade off against one another. The model can fit beautifully while still disagreeing about where the mass truly sits. This sounds straightforward, but the solution is not unique, and that is the central tension. Many orbit mixtures can fit similar kinematic maps, especially when resolution is limited and the central region is undersampled. The model can hide uncertainty inside orbit weights that are difficult to interpret physically. A good fit is necessary, but it is not sufficient. The question becomes whether the fit is constrained by the black hole or merely compatible with it. The critical scale is the sphere of influence, where the black hole's gravity dominates stellar motions over the galaxy's background potential. Its radius is roughly gm over sigma squared, a compact formula with a sharp consequence. If the black hole is huge, the sphere of influence grows, and the signature becomes easier to see. If the galaxy's dispersion is high, the sphere shrinks, and the signature becomes harder. The sphere is not a hard boundary, but it is where the black hole starts to write in bold ink. If we resolve that radius, the black hole leaves a distinct dynamical signature in the central kinematics. The central dispersion rises, and the orbit structure becomes constrained by the need to reproduce that rise. The model can no longer freely swap black hole mass for other components. The data force the solution into a narrower corridor. This is why adaptive optics and space-based imaging matter, even for galaxies that feel close. If we do not resolve it, the black hole's imprint blurs into the galaxy's broader potential, and the measurement becomes a negotiation. Then the mass estimate becomes strongly model-dependent, because different assumptions can reproduce the same smoothed kinematic field. This is where nearby becomes a misleading comfort. The sky does not care about distance in kilometers, only about angles and resolution. A few tenths of an arc-second can decide whether the black hole is measured or merely inferred. For Holmberg 15A, that is the central tension, and it is not a trivial one. The galaxy is large, but the sphere of influence may still be small on the sky, even for an enormous black hole. A massive black hole increases the sphere of influence, which helps, but distance, seeing, and instrument resolution push the other way. The core itself is depleted, so there are fewer stars exactly where we most need kinematic leverage. The very evidence that hints at a giant can also erase the best traces of its pull. When the sphere of influence is comparable to or smaller than the point spread function, the model can trade black hole mass against other ingredients. The fit can look good for very different masses, and the residuals can be equally unconvincing. The telescope smears the central light, and the velocity field is averaged over a region that may include both black hole-dominated and galaxy-dominated zones. In that blended regime, certainty becomes expensive. Even small errors in the point spread function can tilt the result, because the steepest gradients live in the center. One major degeneracy is the stellar mass-to-light ratio, which links observed brightness to gravitational mass. If stars are assumed heavier per unit light, they can mimic some central gravity that would otherwise be attributed to the black hole. This is not a minor technicality, because stellar populations are not uniform. The central regions of massive ellipticals often have different histories than their outskirts. They can be more metal-rich, more alpha-enhanced, and subtly different in their initial mass function. Mass-to-light ratio is not a single number in real galaxies, and that is where the trouble begins. Stellar populations can vary with radius, and gradients can bias the central mass budget in subtle ways. If the center has older or more metal-rich stars, the true mass-to-light ratio can rise inward. Ignoring that can inflate the inferred black hole mass because the model compensates by placing extra mass at the center. A gentle gradient can matter most when the black hole signal is barely resolved. The physics behind this is straightforward, even if the implementation is not. Older stellar populations have a higher fraction of low-mass, dim stars, which add mass without adding much light. Metal-rich populations also alter the spectrum and the inferred stellar mix, affecting template fits and population synthesis. A small systematic shift in mass to light can translate into a large shift in central mass, especially when the black hole signal is unresolved. The uncertainty is not dramatic on a plot, but it can be dramatic in the final mass. Dark matter assumptions add another lever, and in a BCG the lever can be long. A more concentrated dark halo can contribute to the inner potential, depending on the adopted profile and the radius range of the data. If the halo is under-modelled, the black hole can be forced to carry extra gravity. If the halo is over-modelled, the black hole can be driven downward, sometimes dramatically. Cluster centers also host a larger dark matter background, which makes separating galaxy and cluster contributions more delicate. The degeneracy is strongest when kinematics at large radii are sparse, which is common for diffuse galaxies. Without outer constraints, the halo and stellar mass can slide together in the fit, each compensating for the other. The outer data are not glamorous, but they anchor the model's mass distribution. Without that anchor, the center becomes a playground for parameter trade-offs. A BCG's faint envelope can therefore become a key piece of the black hole puzzle. Orbital anisotropy is the third major uncertainty, and it is often the most conceptually slippery. Stars can prefer radial or tangential orbits, and that preference changes the observed dispersion along our line of sight. A tangentially biased core can lower the line of sight dispersion even with a massive black hole. A radially biased core can raise dispersion without needing one, creating a false sense of central mass. The same dispersion profile can be produced by different orbit mixtures, and the galaxy will not tell us which one is correct without extra clues. Schwarzschild models can represent anisotropy, but only as well as the data demand it, and the data do not always demand much. Limited resolution and limited spatial coverage can leave anisotropy weakly constrained, allowing the model to hide mass errors inside orbit structure. This is why higher-order moments of the velocity distribution are valuable. They can reveal whether the dispersion comes from many random motions or from a specific orbit bias. In the best cases, the data can rule out whole families of orbital solutions. This is why giant CD galaxies with large cores are both prime targets and prime traps. They are likely merger products, yet their shallow centers reduce dynamical leverage. A scoured core means fewer stars in the very region where the black hole's gravity is most diagnostic. The measurement becomes a search for a signal in a deficit, and the deficit itself can weaken the signal. The galaxy is telling us a story, but it is telling it in missing words. Holmberg 15A therefore sits at an intersection of clues and uncertainties, which is why it remains so compelling. The core hints at a violent merger past, yet the dynamics must be extracted carefully and interpreted cautiously. The galaxy's smoothness is deceptive, because smoothness can hide complexity. A featureless light distribution can still contain a complicated orbit structure and a layered mass profile. The camera can glide over the pale oval, then pause on the center, where the light stops rising and the questions begin. Some studies reported extremely high black hole masses for Holmberg 15A, and the numbers were difficult to ignore. The claim fit a narrative where core size and black hole mass rise together, implying a direct connection between scouring and black hole assembly. In that narrative, Holmberg 15A becomes a nearby endpoint of hierarchical growth. It becomes the quiet counterpart to early universe quasars, massive for different reasons. The core becomes a ruler, and the ruler seems to point to something extraordinary. Other analyses argued that the same data allow much smaller masses, and they pointed to the same flexibility that makes Schwarzschild modelling powerful. They emphasised modelling choices, resolution limits, and the role of mass-to-light gradients. They also questioned whether the core size alone should be used as a predictor. The debate becomes a lesson in how inference works at the extreme end, where data are precious and models are elastic. When two careful teams disagree, the disagreement itself becomes part of the evidence. This debate is not academic, because it changes the leaderboard of the universe's biggest black holes. It also changes what we think BCGs do at late times, when gas is scarce and mergers dominate. If ultramassive black holes are common in BCGs, then the local universe may hide giants that are simply not shining. If they are rare, then the biggest masses may still belong mostly to the quasar era. Either way, Holmberg 15A forces us to confront how selection shapes our imagination. To interpret Holmberg 15A, we compare dynamical masses to scaling relations, which are empirical shortcuts built from many galaxies. The M-sigma relation links black hole mass to stellar velocity dispersion, a tight correlation for many systems. The M-bulge relation links black hole mass to bulge stellar mass, or luminosity, suggesting co-evolution between black holes and their host spheroids. Both relations are powerful, but both are calibrated mostly on less extreme galaxies. At the top end, we are extrapolating, and extrapolation is where confidence can quietly erode. BCGs can be outliers because their growth is merger-dominated and their envelopes are extended, blurring what bulge even means. Their central dispersions can saturate while their total mass keeps rising, because adding stars to the outskirts does not necessarily deepen the central potential. If sigma stops increasing, sigma may underpredict the biggest BCG black holes. If bulge definitions become ambiguous, bulge can also mislead, because the measured luminosity may include an enormous halo that is not dynamically tied to the core. The relations were built for typical galaxies, and BCGs are not typical. Holmberg 15A's claimed mass sits where these relations are most uncertain, which makes it an ideal stress test. An ultramassive value would place it far above typical expectations, forcing the relations to bend or break at the top end. That could mean BCGs host a distinct population of ultramassive black holes. It could also mean the dynamical inference is being pulled by degeneracies that become severe in shallow cores. The tension is productive because it tells us exactly where our empirical scaffolding is weakest. The core itself becomes part of the argument, and it invites a deeper look at the physics of scouring. If repeated black hole mergers excavate large cores, then core size might correlate with black hole mass, at least in a statistical sense. Yet core size also depends on merger count, mass ratios, and orbital geometry, which can vary widely. It depends on how efficiently binaries harden and whether triples form, because three-body black hole interactions can be especially disruptive. The core is a summary statistic, and summaries always hide details. Gravitational wave recoil adds another layer of complexity, and it is not just a theoretical curiosity. When two black holes merge, asymmetric emission of gravitational waves can kick the remnant, sometimes by hundreds or even thousands of kilometers per second. A kick can displace the merged black hole from the center, stirring the stellar distribution and altering scouring signatures. The displaced remnant can oscillate through the core, heating stars and expanding the deficit further. Subsequent mergers can rebuild a binary and repeat the process, leaving a core shaped by multiple episodes rather than one clean excavation. So a large core is consistent with a huge black hole, but it is not a scale with a single calibration. It is a fossil record with missing pages, and the missing pages matter. We see the final deficit, but we do not directly see the sequence of mergers that produced it. We infer history from structure, and structure can be ambiguous. The most honest reading may be probabilistic, not definitive. Holmberg 15A is also quiet in the electromagnetic sense, and the silence is part of the point. It is not a quasar, and it does not dominate the sky with accretion light. In optical images, there is no glaring point source at the center, no obvious beacon. The galaxy looks like a calm sea of old stars, and the center looks like a calm sea with a subtle depression. The camera can push in slowly, and the absence of a bright nucleus becomes a visual statement. Quiet does not mean small, and this is a key lesson of the chapter, because it separates mass from appetite. Accretion rate and black hole mass are different axes of bigness, and they do not have to align. A black hole can be enormous and nearly starving, especially in a hot cluster environment. The absence of fireworks can be a sign of a different fuel supply, not a different mass. It also raises a question that lingers. How many giants are we ignoring because they are well behaved? At low feeding rates, the accretion flow can be radiatively inefficient, which changes what we expect to see. Energy can stay in the gas and fall inward rather than radiate away, so the luminosity drops even if matter is still moving toward the event horizon. Such flows can be hot, thick and dim, producing little optical or UV emission. The spectrum can shift toward weak radio or faint X-ray signatures, and even those can be intermittent. The black hole can be enormous and still look inactive because the conversion of gravitational energy into light is inefficient. In a cluster center, this inefficiency is plausible because the available gas is often hot and tenuous. Hot gas has high sound speed and high pressure, which can resist collapse into a thin, bright disk. Instead, the flow can remain puffed up and turbulent, leaking energy into mechanical channels like weak jets or winds. That mechanical energy can still matter because it can heat the surrounding gas and discourage cooling. The result is a black hole that may be doing work on its environment without announcing itself with brilliance. This matters for our census of extremes, because selection effects shape what we think exists. The brightest objects are easiest to find, but the most massive objects might not be bright at all. If we build our intuition from quasars, we may miss the quiet giants that live in the nearby universe. The question becomes uncomfortable. How many massive black holes are effectively invisible to surveys that rely on light? A quiet colossus does not volunteer its mass, and it rarely makes a headline. Holmberg 15A therefore represents a different endpoint than TON 618, and the contrast can be staged visually. One is a luminous engine in the early universe, fed by abundant gas and seen across billions of light years. The other is a merger-built relic at a cluster center, grown by repeated coalescences and slow, inefficient feeding. They are two extremes of the same cosmic process, separated by time, environment, and how they reveal themselves. The cut between them can feel like a cut between a wildfire and a glacier, both powerful but in different languages. The cosmological narrative explains why BCGs are plausible hosts for the biggest black holes even when they're quiet, Cluster centers are where galaxies sink, merge, and pile up, guided by gravity over billions of years. Dynamical friction drags massive galaxies inward, bleeding orbital energy into the cluster's background. Each infall can deliver stars, dark matter, and another central black hole, adding to the central system's mass budget. Over time, the BCG becomes a ledger of many arrivals, written into its halo and its core. At late times, gas supply can be limited and hot, reducing luminous accretion and making quasar-like growth rare. Growth by black hole mergers can dominate over bright disk feeding, especially in environments where galaxies collide without much cold gas. In that scenario, the black hole's mass increases in steps, each step a coalescence rather than a feast. The surrounding galaxy grows too, but much of that growth is deposited in the outskirts, leaving the center deceptively unchanged in brightness. The core can widen even as the nucleus stays photometrically quiet. If that is true, the biggest masses might be found in quiet cores, not in blazing quasars, and that possibility reshapes the search. The universe's largest black holes could be hardest to notice, because they are not advertising their presence. They would be inferred from subtle dynamical signatures and from the scars they leave in stellar distributions. The quiet colossus becomes a detective story rather than a spectacle. The evidence is not a flare but a deficit, and deficits require patience. But the measurement must still be earned, and the standards must be high, because extraordinary masses demand extraordinary constraints. To confirm an ultramassive black hole, we need kinematics that resolve the sphere of influence, not merely brush against it. We need inner data with high spatial resolution and outer data that constrain the stellar mass and dark halo. We need models that test population gradients and anisotropy, rather than assuming them away. The most persuasive result is the one that survives hostile assumptions. We also need cross-checks that do not share the same assumptions, because shared assumptions can produce shared errors. Independent tracers like gas disks, globular cluster dynamics, or planetary nebulae can help, especially at larger radii where starlight is faint. Each tracer has its own complications, but together they can triangulate the potential. A robust mass estimate is not a single measurement, it is a convergence. When different methods agree, the agreement becomes its own kind of signal. Even then, the top end may remain uncertain because the systems are complex and complexity is not noise. The most massive galaxies are not simple ellipsoids with uniform stars, and they may not be perfectly axisymmetric. Their centers can contain subtle twists, traxial shapes, or remnants of past interactions. Small departures from symmetry can shift orbit families, and orbit families can shift inferred mass. When we model them as smooth and regular, we are simplifying reality in ways that can matter. So we hold the suspense where it belongs, because the story is not settled by a single number. Holmberg 15A might host one of the largest black holes ever measured, or it might be a cautionary tale about inference at the edge of resolution. The same core that invites a bold claim also warns us about missing information. The galaxy looks calm, but the measurement is not. The camera can rest on that calmness, letting the audience feel how deceptive it can be. If the mass is truly tens of billions, it strengthens the case that mergers can build ultramassive giants in the modern universe. It ties core scouring to black hole assembly, and it suggests that the quiet era can still produce extremes. It would imply that the local universe contains black holes comparable to the quasar-era titans, but hidden behind inactivity. It would also challenge models of feedback and galaxy evolution, because such a mass must fit into the broader cluster ecosystem. How does a cluster regulate a central object that massive without lighting it up? If the mass is lower, it warns us that shallow cores and limited resolution can exaggerate the central mass, even when the modelling is sophisticated. It forces humility about dynamical inference, reminding us that flexibility can mimic certainty. It would still leave Holmberg 15A as an important merger relic, but not necessarily a record holder. The lesson would shift from largest to hardest to measure, which is a different kind of extremity. That extremity is methodological, and it matters just as much for what we believe. Either outcome feeds the film's central question, and the question is not only about size. How big can black holes truly get, and which environments make that growth plausible? The answer depends on fuel, on mergers, on time, and on the physics that governs how binaries harden and merge. It also depends on how well our measurements can separate black holes from the galaxies that surround them. When the evidence is subtle, our own assumptions become part of the experiment. TON 618 shows how early gas feeding can create a luminous giant under time pressure, when the universe is young and dense. Phoenix A shows how cluster atmospheres can regulate growth through feedback, where energy output reshapes the fuel supply. Holmberg 15A asks whether the final stage is quiet accumulation through mergers, leaving a scoured core as the signature. It is a giant written in missing starlight, and the missing starlight is the clue we must learn to read. The most dramatic moment may be the one where nothing seems to happen, yet everything has already happened. Now that we have met 3 contenders, the comparison becomes the real problem, because each contender is measured in a different language. Different methods weigh different kinds of evidence, and each has its own failure modes, its own blind spots. A quasar mass can be biased by assumptions about broadline regions and orientation. A dynamical mass can be biased by resolution, anisotropy, and population gradients, even when the data look precise. The film's mystery sharpens here, because the uncertainty is not ignorance, it is structure. We move from individual case files to a harder question about limits, and the tone must tighten without losing mystery. How do we compare largest across methods, and what are the true physical ceilings? The next chapter tightens the ladder of inference step by careful step. We confront systematics directly and ask what the universe allows, not just what our catalogues list. Now that we have met 3 contenders, the comparison becomes the real problem. The central question sharpens, because the numbers alone are not the story. How big can black holes truly get, and what limits the climb? Black holes do not face a hard cap like neutron stars where degeneracy pressure fails at a fairly specific threshold. There is no single density limit that forces collapse into something else, because the something else is already the endpoint. The ceiling is practical, and it is messy. It is fuel, time, and the backlash from the energy released. In the early days of relativistic theory, black holes were treated like mathematical curiosities, and even the term itself arrived late. By the time quasars were discovered in the 1960s, the question changed from do they exist to how can anything shine like that? The modern answer is accretion, and accretion is a supply problem. If the universe can keep delivering mass to the center, the black hole can keep growing. If it cannot, the growth curve flattens. To grow, a black hole needs a supply chain that stays unbroken for long periods, and it must survive its own side effects. The chain starts on cosmic web scales, where filaments funnel gas into dark matter halos like rivers into a basin. It continues through galactic scales, where mergers, bars, and spiral torques can drain orbital energy and push gas inward. It ends in the nucleus, where angular momentum and heat decide what reaches the disk. On screen, this chain is easiest to imagine as nested flows. First, a wide shot of the cosmic web, thin, luminous threads traced by faint hydrogen emission and galaxy light. Then the camera dives into a halo, where gas shocks, cools, and swirls into a rotating structure. Finally, the view narrows to the central kiloparsec, where dust lanes twist like braided ropes and the last obstacles appear. This supply chain fails in predictable places, and the failures are not subtle. Gas arriving from filaments carries angular momentum that resists direct infall, because rotation is an efficient way to store energy. It must shed that momentum through torques, turbulence, and instabilities, or it stalls at larger radii. Even when gas reaches the inner hundreds of parsecs, star formation can intercept it and lock it into stars. Angular momentum is the quiet antagonist of black hole growth, because it turns a simple fall into a long negotiation. A parcel of gas cannot just drop straight down, since even a small sideways velocity becomes dominant as the radius shrinks. The gas must trade angular momentum outward, often through gravitational torques from bars or tidal distortions during mergers. In plain terms, the gas needs friction, but in space, the friction is collective gravity and turbulence. The nucleus is a bottleneck that turns geometry into destiny, and the geometry is set by cooling physics. A thin disk forms when gas cools efficiently and settles into rotation, creating a bright, compact engine. A thick, hot flow forms when cooling is weak and turbulence dominates, producing a puffed-up structure that radiates less per unit mass. Both can feed a black hole, but they feed it differently, and they broadcast different feedback. A thin disk is visually cinematic because it is orderly and sharp-edged. You can picture it as a luminous record groove with hotter, bluer light closer to the center. A thick flow looks more like a storm, eddies, shocks, and magnetic loops that rise and reconnect. The difference matters because radiation and winds escape differently from each structure, and that changes how the environment responds. The Eddington limit is not a wall, and it is not a law that forbids brightness. It is a balance between gravity pulling inward and radiation pressure pushing outward on electrons in ionized gas. When photons scatter off electrons, they transfer momentum, and enough momentum can counteract gravity. The limit sets a typical growth pace when radiation couples well to inflowing gas. It also sets a timescale that becomes a recurring beat in this story. If a black hole accretes steadily at the Eddington rate with a typical radiative efficiency, it grows exponentially with a characteristic e-folding time, often called the Salpeter time. That number is not magic, but it is a yardstick. To reach tens of billions of solar masses, a black hole needs many such e-folds, and it needs them early. The largest black holes can exceed the Eddington rate briefly through slim disks and photon trapping, where radiation is carried inward with the flow. In that regime, the luminosity does not rise in proportion to the mass inflow, because photons struggle to diffuse outward. Yet winds and geometry often erase the advantage, because excess inflow tends to drive powerful outflows. Super Eddington growth is possible, but it is rarely clean. The real upper bound is the product of duty cycle and cosmic time, because growth requires persistence. A black hole must stay fed at high rates for many salpeter times, not merely flare once and fade. That requires a host that keeps delivering gas despite star formation, heating, and outflows. It also requires that feedback does not cut the line. Duty cycle sounds like bookkeeping, but it is the difference between a giant and a merely large black hole. If accretion happens in short bursts separated by long droughts, exponential growth never gets traction. If accretion stays high for hundreds of millions of years, the mass curve steepens dramatically. The universe provides both kinds of histories, and our three contenders hint at each. Feedback is the universe's throttle, and it is the reason more fuel does not automatically mean more growth. Accretion releases energy, and that energy pushes back on the same gas that would otherwise feed the disk. The result is self-regulation, not because nature prefers balance, but because imbalance is unstable. If the black hole overfeeds, it tends to shut its own faucet. The energy budget is enormous, even when only a modest fraction couples to the surroundings. A few percent of rest mass energy is enough to rival the binding energy of a galactic bulge. That is why black holes can influence galaxies while being tiny in mass fraction. The paradox is that the smallest component can set the thermostat for the whole system. This is why black hole mass correlates with bulge properties, and why those correlations were so striking when they emerged. The bulge is the gravitational container that sets escape speed and binding energy, and it also sets how easily gas can be lifted or heated. When feedback can unbind or heat the bulge gas, growth slows. When the bulge deepens, the black hole can grow larger before feedback becomes decisive. Historically, these correlations were not obvious because black holes were hard to weigh. As stellar dynamical measurements improved in the 1990s and early 2000s, patterns appeared between black hole mass and stellar velocity dispersion. The relationship suggested a coevolution, or at least a shared regulation mechanism. It raised a question that still hangs in the air. Are galaxies building black holes, or are black holes sculpting galaxies? Two feedback pictures frame the intuition, and they are useful because they reduce complicated physics into testable scaling. Momentum-driven feedback treats radiation and winds as a push that must overcome gravity, like a steady shove against a heavy door. Energy-driven feedback treats the outflow as a hot bubble that does work on surrounding gas, like a blast that inflates and expands. Both predict scaling links between black hole mass and host depth, but they differ in coupling and efficiency. In momentum-driven limits, the black hole grows until its thrust balances the weight of gas in the bulge, and the math ties that to velocity dispersion. In energy-driven limits, the black hole grows until it can heat or expel gas faster than it cools and falls back. Real galaxies mix both regimes, and the transition depends on cooling, density, and geometry. Cooling is the hinge, because it decides whether injected energy stays as heat or radiates away quickly. Dense gas can cool so efficiently that it shrugs off heating, forcing feedback to rely on momentum and direct driving. More diffuse gas can be kept hot, allowing energy-driven bubbles to expand and do work. The same black hole can therefore operate in different modes across time. Phoenix A is the feedback story written at cluster scale, where the environment is both generous and unforgiving. The intracluster medium is a giant reservoir, but it is also a giant heat sink that can swallow energy without dramatic motion. Cooling tries to deliver fuel through precipitation and cold filaments, which can appear as narrow tendrils in optical and infrared light. Jets inflate cavities and raise entropy, and the core becomes a thermostat with delays. Visually, the cluster core is a layered scene. X-ray light outlines the hot plasma like a ghostly fog, while radio maps trace the lobes of relativistic particles. Cavities appear as dark bubbles carved into the X-ray glow, often rimmed by brighter shells where gas has been compressed. The sense is of a slow, continuous struggle, not a single explosion. Phoenix also shows that regulation can be imperfect, because the feedback loop is not instantaneous. Jets can miss the densest cooling region and deposit energy at larger radii, leaving the center free to cool again. Cooling can surge between outbursts and build a cold reservoir that feeds both stars and the nucleus. The limit is not only power, it is where the power lands. This where it lands problem is a geometric one, and geometry is often destiny in astrophysics. A jet is narrow, and the cooling region can be clumpy and asymmetric. If the jet drills through low-density channels, it can heat the outskirts while the core continues to condense. The cluster then behaves like a thermostat with a lag, overshooting and undershooting around a moving set point. TON 6-18 is the opposite extreme, and the contrast is part of the chapter's tension. It is a luminous quasar whose mass is inferred through broad lines and empirical radius relations, not through resolved motion. Its growth demands sustained feeding in the early universe, when gas was abundant and mergers were frequent. Its limit is not a lack of fuel alone. Its limit is whether feedback and angular momentum allow that fuel to stay coherent. A quasar scene is bright, compact, and deceptive. The central engine is smaller than our solar system in scale, yet it outshines an entire galaxy. Broad emission lines form in fast-moving gas clouds, and their widths encode velocity, but only if the motion is gravitational. Winds can widen lines, and orientation can hide the true geometry. Holmberg 15A represents the late-time path, where the universe has cooled into a quieter rhythm. Gas is scarce and often hot, so luminous accretion can be weak and intermittent. Mergers can still add mass in steps, while binaries scour out stellar cores and reshape the center. The limit becomes merger frequency, retention after kicks, and whether the nucleus can keep a central black hole anchored. In images, this kind of galaxy looks like a pale, swollen lantern, with a core that seems strangely underlit. The light profile can flatten, hinting that stars have been displaced from the center. That depleted core is a fossil record of past interactions, written in missing starlight. It suggests that growth can continue even when gas feeding has largely ended. These three cases imply that the largest masses are built by different mixes of feeding and merging, depending on era and environment. Early quasars emphasize rapid gas delivery and high duty cycle, with intense accretion episodes that may repeat. Cluster cores emphasize long-lived reservoirs and feedback cycles that can persist for billions of years. BCG relics emphasize hierarchical assembly and the quiet accumulation of black hole mass. The implication is unsettling because it means there may not be a single path to the top. The universe can build giants through sustained radiative growth, or through mergers that add mass without much light. It can also build them through a hybrid sequence where early accretion sets the foundation and later mergers finish the job. If so, the maximum mass is not one number, but a family of histories. Spin is the hidden variable that changes the rules mid-game, and it is easy to overlook because it is harder to measure. A black hole's spin sets the innermost stable orbit and the radiative efficiency of accretion, which is the fraction of rest mass turned into energy. High spin extracts more energy per unit mass, brightening the disk and strengthening feedback. That same efficiency can slow mass growth at fixed luminosity, because more rest mass becomes light. This is one of the chapter's quiet reversals. A more efficient engine can build mass more slowly, because it spends more of its fuel on radiation. If two black holes shine at the same luminosity, the one with higher efficiency needs less mass inflow. Over cosmic time, that difference accumulates, and it can shift the upper envelope of growth. Spin therefore matters even when we cannot see it directly. Coherent accretion tends to spin black holes up, and the mechanism is straightforward. If gas arrives with a stable angular momentum axis, the disk aligns and adds spin steadily, like pushing a carousel in the same direction. Chaotic accretion tends to spin black holes down, or at least keep spin modest. If gas arrives in short, misaligned episodes, angular momentum cancels over time and the net spin can remain moderate. The alignment itself is a subtle, relativistic effect, because a spinning black hole drags spacetime around it. That frame dragging can twist the inner disk and help it align with the spin axis, creating a more coherent configuration. Yet coherence is fragile, because galaxy-scale inflows are rarely perfectly steady. The supply chain can arrive in bursts, and each burst can tilt the disk. Mergers complicate spin further, because they combine two rotating horizons into one. Comparable mass mergers can produce a remnant with high or moderate spin depending on orientations, and the outcome is sensitive to the initial configuration. Repeated mergers in random directions can keep spin from saturating, even if individual events are dramatic. Spin history is therefore a record of how ordered the supply chain has been. Spin also controls jets through the Blandford-Znajek mechanism, which is one of the most elegant ideas in high-energy astrophysics. Magnetic fields threading a spinning horizon can extract rotational energy and launch powerful relativistic jets. If spin is high and magnetic flux is large, jets can dominate the feedback budget. If spin is low or flux is weak, feedback may be more wind-driven or radiative. The visuals here are stark and geometric. A dark central silhouette, a bright ring of emission, and twin beams punching outward at near light speed. Along the jets, shocks and knots mark where energy is dissipated into particles and fields. At larger scales, the jets inflate radio lobes and carve cavities, leaving fingerprints that can persist long after the engine varies. This creates a tension that matters for maximum mass, because the traits that make a black hole powerful can also make it self-limiting. High spin can power strong jets that heat and expel fuel, limiting further growth in gas-rich phases. Low spin can allow more mass growth per unit luminosity, because less energy is radiated away. Yet low spin may reduce mechanical leverage, changing how feedback couples. The largest black holes may therefore prefer a mixed history, with phases that spin up and phases that spin down. They may grow rapidly in chaotic episodes that keep efficiency modest, then later enter coherent phases that launch strong jets and stabilize the environment. Or the sequence could reverse, depending on when gas arrives and when mergers dominate. The point is that spin is not decoration. It is a control knob. A second ceiling comes from merger statistics, and it is a ceiling made of probability rather than physics. The biggest black holes often live in the biggest galaxies, and those galaxies live in dense environments. Yet merger rates decline with cosmic time as the universe expands and structures relax. In clusters, high relative velocities can suppress galaxy merging, even while galaxies crowd together. This is a counterintuitive scene, many galaxies in close proximity, yet fewer effective mergers. Fast flybys do not dissipate enough orbital energy to bind, so they pass like ships in a storm. In smaller groups where velocities are lower, mergers are easier, and central galaxies can grow by cannibalizing neighbors. The environment therefore shapes the merger ladder. When mergers do occur, gravitational wave recoil can undo the gain, and the mechanism is purely relativistic. Asymmetric wave emission can kick the remnant black hole at hundreds or thousands of kilometers per second. A kick can displace the remnant from the nucleus, starving it of dense fuel. In smaller galaxies, a strong kick can eject it entirely, erasing the growth line. Recoil is not just a theoretical flourish, because it follows from conservation of momentum. Gravitational waves carry momentum away, and if the emission is lopsided, the remnant must recoil. The kick depends on mass ratio and spin orientation, which ties it back to the earlier spin story. The same spin that powers jets can also set the recoil geometry. Retention therefore becomes part of the maximum mass problem, and it introduces a new kind of selection. Deep potentials in BCGs help hold kicked remnants, allowing oscillations that eventually damp through dynamical friction. Shallow potentials lose remnants more easily, which can cap growth and increase scatter. The largest black holes should be biased toward the deepest wells, where escape speeds are highest. Recoil also reshapes the stellar core, leaving signatures that can mislead or enlighten. A displaced black hole can heat the central stars and expand the depleted region, changing the inner light profile. That can mimic or amplify core scouring signatures from binaries, making the core look older or more violent than it was. It can also complicate dynamical mass inference, because the central phase space has been stirred. At this point, the story turns on what we mean by largest, because largest is partly an observational category. Our catalogues are not the universe. They are the subset that our methods can detect and our models can interpret. Selection effects decide which giants become famous. Luminous quasars are easy to find across cosmic distance, because brightness is a beacon. Their light cuts through the expanding universe, and surveys can flag them by colour and variability. Spectra provide broad lines for virial mass estimates, and the method scales well to high redshift. Yet the mass is indirect, calibrated on lower mass systems and sensitive to geometry, winds and orientation. A bright quasar can be overweighed if the line width includes outflow components that are not bound motion. It can be underweighed if the broadline region is flattened and seen face-on, hiding true velocities. Radiation pressure can also alter cloud dynamics, subtly biasing the virial assumption. Even lensing can intrude because magnification can make an object seem intrinsically more luminous than it is. Dormant giants nearby are harder in a different way because they do not announce themselves with light. They require resolving a tiny sphere of influence against a bright stellar background. Angular resolution and point spread function control whether the black hole imprint is separable from the galaxy's own gravity. Even with good data, anisotropy and mass-to-light gradients can trade off with black hole mass. The sphere of influence is a simple idea with a cruel requirement. It is the region where the black hole's gravity dominates over the stars, and its angular size shrinks quickly with distance. If the sphere is smaller than the telescope's effective resolution, models can fit many masses equally well. The black hole becomes a parameter that absorbs uncertainty. Cluster center systems add another bias, because their black holes can be constrained by feedback energetics rather than direct kinematics. Cavity power constrains accretion history and efficiency, not the horizon mass itself. Scaling relations at the top end may break, and BCG structure makes bulge definitions ambiguous. In these systems, even defining the bulge can become a modelling decision. So largest known is not largest existing, and that gap is the chapter's lingering mystery. It is largest that our methods can currently defend, with error bars that survive scrutiny. The leaderboard is therefore provisional, and the film's mystery is partly a measurement story. The universe may hide heavier objects in quiet galaxies, or in obscured phases we rarely catch. Comparing the three requires comparing methods, not just numbers, because each number is a ladder of inference. TON 6 and 18 relies on quasar-virial masses and radius, luminosity extrapolations. The uncertainty is dominated by broadline physics, orientation, and possible lensing. Phoenix A relies on environment and feedback constraints, with mass inferred through scaling and energetics. Holmberg 15A relies on stellar dynamics, with uncertainty driven by resolution, anisotropy, and stellar population gradients. Each method fails differently, which is why agreement matters. If multiple independent routes converge, confidence rises, because shared bias becomes less likely. If they diverge, the divergence is information, not embarrassment. It tells us where the ladder is weakest, and where physics or calibration must be revisited. This is also where the extreme density paradox returns with force, because it reframes what giant means. As black holes get more massive, the average density inside the horizon drops. The horizon volume grows faster than the mass, so the mean density declines with increasing mass. A stellar mass black hole is unimaginably dense. A tens of billions solar mass black hole can have an average density that feels almost ordinary. Conceptually, it can be compared to air at sea level, and the comparison is meant to unsettle intuition. The point is not the exact number, because the horizon is not a material surface. The point is the scaling that breaks the mental picture of a black hole as a tiny ultra-dense bead. The biggest black holes are not dense needles. They are vast, low-average density regions where space-time is so warped that escape is impossible. On screen, this is a chance to slow down and let scale do the work. A translucent sphere expands until it dwarfs planetary orbits, while a mass counter climbs more slowly than the volume. The narration can linger on the idea that density is an average over a region defined by geometry. Inside the horizon, the rules of ordinary comparison stop being comfortable. That counterintuitive scaling matters for observation, because size does not automatically mean visibility. A larger horizon is easier to resolve in angle only if the black hole is close, and distance usually wins. The giants we suspect, like TON 618, are too distant for horizon imaging with current baselines. The giants we can image, like M87 Sin, are not the most massive candidates, but they are nearby enough to test strong gravity directly. This mismatch shapes our confidence. We can measure horizon scale structure for nearby objects, but those objects may not sit at the top of the mass distribution. We can infer enormous masses for distant quasars, but we cannot yet see their horizons. The frontier is therefore split between direct tests of relativity and indirect reconstructions of mass. So what would falsify current claims, and what would strengthen them without changing the story? For TON 618, improved spectroscopy can separate virial motion from winds and line asymmetries, reducing the risk of inflated line widths. Better reverberation mapping at high luminosity can anchor the radius-luminosity relation where it is now extrapolated. Independent mass checks through multi-line consistency and improved SED modeling can reduce orientation and radiation pressure biases. There is also a simple observational discipline here. Do different lines tell the same story? If hydrogen lines, carbon lines, and magnesium lines imply different masses, the broad line region is not behaving like a clean virial tracer. If variability timescales contradict the inferred size, the calibration is off. Each inconsistency is a clue about geometry, not merely an error. For Phoenix A, better constraints on the host galaxy's dispersion and stellar mass can tighten scaling estimates, because the current argument leans on host depth. Deeper X-ray mapping of cavities, shocks, and ripples can refine the mechanical power history and the coupling radius. If the calorimeter budget demands implausible efficiencies, the assumed mass or accretion mode must change. In other words, the cluster can be treated like an energy ledger, but only if we can read the entries clearly. How much energy is in the cavities, and how fast were they inflated? How much is in weak shocks, sound waves, and turbulence? If the heating channels add up cleanly, the feedback story holds. If they do not, either the black hole is different than assumed, or the coupling physics is incomplete. For Holmberg 15A, the test is resolution and coverage, because dynamical inference is only as good as the kinematic map. Higher resolution integral field spectroscopy can resolve the sphere of influence and constrain anisotropy with higher moments. Better stellar population modeling can map mass-to-light gradients instead of assuming a constant value. Wider field kinematics can anchor the dark halo and reduce degeneracies that inflate central mass. The key is to prevent the model from using the black hole as a substitute for missing information. If the outer halo is poorly constrained, the central mass can absorb the mismatch. If stellar orbits are assumed too isotropic, the black hole can be overestimated. Better data reduce the space of equally good fits, and the mass becomes less negotiable. Rare methods could provide decisive cross-checks, and their rarity is part of the drama. Massa disks can yield geometric masses with minimal modeling because the rotation curve is directly measured. Yet masses require specific conditions, and they are uncommon in BCGs and giant ellipticals. Gas disk dynamics can help if a cold, thin disk exists and is not disturbed by feedback. Globular cluster and planetary nebula kinematics can constrain outer potentials, reducing halo trade-offs. Future instruments will change the census, and they will change it unevenly, because each technique benefits differently. Extremely large telescopes will push stellar dynamics to finer angular scales, resolving spheres of influence in more distant BCGs. Adaptive optics will sharpen central kinematics and reduce point spread uncertainty that currently blurs the key region. The result will be a larger sample of dormant giants with defensible masses. Advanced X-ray observatories will map intracluster feedback with higher spectral resolution and sensitivity, turning vague impressions into measured flows. They will measure turbulence, bulk motions, and shock heating more directly, rather than inferring them from morphology alone. That will tighten the energy accounting that underpins cluster feedback arguments. It will also reveal whether systems like Phoenix are rare phases or common but short-lived states. Gravitational wave detectors will open a new channel for the biggest mergers, and this channel bypasses many electromagnetic ambiguities. LISA will detect massive black hole mergers across cosmic time, measuring masses and spins directly from the waveform. It will also measure recoil-related asymmetries indirectly through spin orientations and mass ratios. This will test whether mergers can build the top end without ejecting remnants. The appeal is that the waveform is a clean messenger, because it encodes the system's parameters in its phase evolution. Distance, redshift, and mass are intertwined, but the signal carries enough structure to disentangle them. Spin precession can reveal whether spins were aligned, which feeds back into recoil expectations. The growth history becomes something we can hear, not just infer. Event Horizon telescope extensions will probe horizon-scale structure for nearby giants, refining the direct view of strong gravity. More stations and higher frequencies will improve resolution and imaging fidelity, and they will reduce the ambiguity of sparse sampling. Yet feasibility has limits, and the film should admit them. Distant ultramassive candidates will remain too small in angle, and scattering and sensitivity will still constrain targets. As these tools arrive, the meaning of largest will shift again, because the measurement floor will move. Some objects will move down as systematics shrink and calibrations tighten. Others will move up as dormant giants are uncovered in galaxies that never hosted a famous quasar phase. The record holder may change, but the deeper pattern should become clearer. The pattern is a dialogue between gravity, environment, and time, and each term is non-negotiable. Gravity sets the possibility of collapse and the scale of the horizon, and it also sets the binding energy that feedback must overcome. Environment sets the fuel supply chain and the coupling of feedback, deciding whether energy escapes or is trapped. Time sets how many growth cycles can occur before the universe thins out and merges slow. This is the limit of gigantism, and it is not a single forbidden mass written into the equations. It is a narrowing corridor of plausible histories, shaped by supply logistics and self-inflicted resistance. To reach tens of billions of solar masses, a black hole must be born early enough, fed long enough, and protected from its own power. It must live where the supply chain is rich and where the host is deep enough to keep it centered. We return to the hook with a colder clarity because the romance of largest has been replaced by constraints. Somewhere in the deep past, something grew so massive it could swallow our solar system's scale in shadow, and yet it may have done so quietly. We do not know it by sight. We know it by the way it organizes everything around it, and by the limits it forces us to confront. With limits and uncertainties laid bare, we can finally assemble a coherent answer. The final chapter will weigh the contenders, reconcile methods, and state what the largest black holes mean. The mystery does not end with a number. It ends with a map of how the universe builds its biggest structures, using darkness as its most faithful record. We return to the hook with a harder promise, because the deep past sometimes leaves only fingerprints. Somewhere in that past, something grew so massive its shadow could span planetary orbits, and yet we only know it through effects. To answer how big, we must restate what big means, because black holes resist ordinary intuition. A black hole has no surface, no crust, no glowing boundary, so size becomes a story told through gravity and light. Mass is the primary measure because it sets every other scale, from orbital speeds to radiation limits. In general relativity, mass curves space-time, and that curvature dictates what paths matter and light are allowed to take. Horizon size follows mass almost linearly, which is why astronomers like it as a translation tool. Double the mass and you roughly double the Schwarzschild radius, even though nothing like a solid object is growing. Average density can drop as mass rises, and that fact is as unsettling as it is true. When you spread mass across a horizon that expands faster than volume intuition suggests, the mean density can become lower than water. The event horizon is a geometric boundary, not a material edge, and that distinction matters for every visual we imagine. It is the place where escape routes end, where outward-pointing light cones tilt inward, and where out stops being a direction. For a non-spinning hole, the Schwarzschild radius scales with mass and sets the simplest yardstick. It is a clean formula, born from Karl Schwarzschild's 1916 solution, and it remains the baseline for our comparisons. Yet even this simplest yardstick can mislead the mind because the horizon is not a wall. A falling object does not smash into a surface. It simply crosses a boundary that distant observers can only infer through delayed signals. Spin complicates the picture without changing the core idea, because rotating space-time adds structure. A fast-spinning Kerr hole has a smaller horizon, an ergosphere where space-time is dragged around, and a different innermost stable orbit. That innermost stable orbit matters because it sets how efficiently accretion can turn infall into energy. If gas can orbit closer before plunging, more gravitational potential energy can be released as heat, light, winds, and jets. Influence is a second kind of size, and it is often what we can measure with less interpretation. The sphere of influence is where the black hole's gravity dominates stellar motions over the host galaxy's broader potential. In practice, that sphere is not a crisp bubble, but a region where competing gravitational contributions trade places. Stars feel the pull of the black hole, the surrounding stellar mass, and dark matter, and we disentangle them by modelling. A third kind of size is energetic reach when the hole is active because power can travel far. Accretion converts infall into radiation, winds, and jets that can heat gas far beyond the horizon, sometimes across an entire cluster core. Even that energetic reach has multiple channels, and each leaves different evidence in telescopes. Radiation ionizes and pushes, winds shock and stir, and jets carve cavities that remain long after the central engine dims. These definitions matter because our three giants are measured in different languages, with different contracts and different loopholes. The ranking depends on which size we mean, and on how much inference we allow. Now, we synthesize the portrait starting with the earliest challenge, because it tests the universe's first growth steps. TON 618 is a quasar seen at great distance, so we weigh it through spectra and calibrated relations. Visually, the quasar is a point of fierce light, but the spectrum is a coded landscape of lines and slopes. Broad emission lines smear across wavelengths, and their widths hint at orbital speeds in gas bound to the central mass. Its mass estimate comes from broad line widths and an inferred radius for the broad line region. That radius is not usually measured directly at such distances, so we use luminosity-based scaling built from nearer reverberation-mapped quasars. Reverberation mapping is itself a clever workaround, and it has a history of turning time delays into distance. When the continuum brightens, the broad lines respond later, and that lag gives the light travel size of the emitting region. That ladder depends on virial assumptions, geometry, orientation, and how winds contaminate line profiles. If the gas is not purely orbiting, or if we view a flattened region at a special angle, the line widths can mislead. Even the choice of which line to trust can matter, because different ions live in different zones. Some lines are more affected by outflows, while others track more gravitationally bound gas, and the calibration must be chosen carefully. Even with those caveats, TON 618 remains a serious ultramassive candidate because the numbers refuse to shrink easily. It sits in the billions to tens of billions solar mass regime, and it strains early universe growth timelines. The tension is not only the final mass, but the clock, because cosmic time is short at high redshift. When we see a quasar far away, we see it when the universe was young and the available E-foldings of growth are limited. To reach that scale quickly, it needs massive seeds, sustained high-duty cycle, super Eddington phases, or mergers that arrive early. Each option has consequences for what the first galaxies looked like and for how violently they evolved. The Eddington limit is the balancing act that makes the problem sharp in plain language. Too much radiation pushes infalling gas away, so sustained rapid growth requires either special geometry, dense inflows, or brief episodes that break the usual rule. TON 618 therefore becomes a test of supply chains in the young cosmos, not just a test of measurement technique. It implies rare conditions where fuel delivery stayed coherent despite feedback that should have throttled the flow. Picture cold gas streaming along filaments into a forming halo, feeding a nucleus that is already bright enough to fight back. The question is whether the inflow can stay clumpy and persistent, or whether the quasar's own output shreds it. We pivot from the quasar's glare to a cluster core we can map, where the evidence is written into hot gas. Phoenix A is not famous because we see its horizon, but because we see its environment respond. The Phoenix cluster is a cathedral of plasma glowing in X-rays where temperatures reach tens of millions of degrees. In images, the core looks like a bright ember surrounded by diffuse haze, and that brightness signals rapid radiative cooling. Phoenix sits in a cooling flow battleground, where hot intracluster gas radiates rapidly in the core. For decades, astronomers expected that cooling gas would rain down and form stars, yet many clusters showed missing cooling signatures. The missing cooling flow signatures elsewhere make Phoenix's starburst and condensation especially telling. Here, the core seems to cool more efficiently than usual, and the central galaxy forms stars at a rate that forces us to confront the balance again. In this setting, bigness is inferred through power and regulation, not direct dynamics. Cavities, shocks, and radio jets act like a calorimeter, letting us estimate mechanical work over time. A cavity is a void blown into the X-ray gas, and it carries an energy budget we can approximate. The surrounding pressure tells us how much work was done, and the cavity's size hints at how long the jet kept pushing. Shock fronts add another layer, because they are moving boundaries where gas is compressed and heated. In a good X-ray map, they appear as arcs or edges, like ripples in a pond, except the pond spans hundreds of thousands of light years. Phoenix A is a feedback engine, and its size shows up as influence over thermodynamics. When active, it can rewrite entropy profiles, suppress cooling, and shape star formation in the central galaxy. Entropy here is not an abstract classroom quantity, but a practical record of heating and mixing. Raise it and gas resist condensation, lower it and gas can sink, cool, and feed both stars and the black hole. Yet Phoenix also shows feedback can be mistimed or misaimed, which is a subtle but crucial point. Jets may deposit energy at larger radii while the inner core keeps cooling, creating a loop that slips instead of stabilizing. Visually, it is like heating the outer layers of a storm while the eye continues to intensify. The cluster core can keep forming cold clouds, and those clouds can keep delivering fuel, even as the jets roar elsewhere. Its mass is therefore uncertain in a specific way, because the environment tells us power more readily than it tells us gravity. Scaling relations and host properties suggest a very large black hole, but the top end is sparse and BCGs are structural outliers. Brightest cluster galaxies have unusual histories, built by repeated mergers and enveloped by intracluster light. Their stellar profiles can be extended and cored, which complicates the usual correlations between black hole mass and bulge properties. Phoenix adds a different constraint on maximum growth, because it highlights the gatekeeping role of hot atmospheres. Even if fuel exists, the environment decides whether it reaches the center and whether the released energy cuts the line. We pivot again from loud heating to quiet starlight, where the clues are subtle and slow. Holmberg 15A offers a possible ultramassive relic built by mergers, hinted by a depleted core and a long assembly history. In images, the galaxy's center looks strangely flattened, as if starlight has been scooped out. That depleted core is the kind of fossil feature that does not need an active quasar, only time and repeated gravitational encounters. In this case, the measurement goal is direct gravity through stellar dynamics, and that goal is demanding. We infer mass from the velocity distribution of stars, then model the potential with stars, dark matter, and a central black hole. The raw data are spectra again, but now the story is in tiny shifts and broadenings across the galaxy's face. Each spatial element carries a line-of-sight velocity distribution, and together they form a kinematic map. The method is powerful, and the uncertainties are structural, because galaxies are not simple spheres. Resolution, point spread function, orbital anisotropy, and mass-to-light gradients can trade off with black hole mass. Orbital anisotropy is a technical phrase with a simple meaning. Stars may prefer certain directions of motion. If more stars move radially than tangentially, the same observed dispersion can be fit with a different central mass. Mass-to-light gradients add another degeneracy, because stellar populations change with radius. If the central region has different stellar ages or metallicities, the light does not translate into mass the same way everywhere. The depleted core is both clue and complication, which is why this case sits at the edge of confidence. It suggests past black hole binaries scoured stars outward, yet it also removes the very central traces that best reveal the black hole. That scouring has a physical mechanism that is almost cinematic in its simplicity. As two supermassive black holes spiral together, they fling nearby stars outward through gravitational slingshots, excavating a low-density core. Holmberg 15A therefore represents a late-time pathway, where growth is slow and cumulative rather than explosive. If its central mass is truly extreme, it supports growth by repeated dry mergers in deep cluster potentials. Dry mergers matter because they bring stars and black holes without much cold gas, so there may be little quasar light. The mass can climb while the galaxy stays relatively quiet, and the evidence is left in structure. If the mass is lower, it still teaches the same lesson at the edge, because the modelling is a stress test. The largest claims are where models are most elastic and where the sphere of influence is hardest to resolve. That sphere of influence shrinks on the sky with distance, which is a practical limit that feels almost unfair. Even a gigantic black hole can hide if its decisive region spans only a few pixels, blurred by Earth's atmosphere and optics. With the portraits assembled, we can answer the ranking question carefully, because the temptation to crown a winner is strong. We should not ask for a single definitive leaderboard, because each candidate carries method-dependent systematics. Instead, we ask what regime is defensible across uncertainties, and we treat the numbers as ranges with histories. The largest black holes appear to reach at least the tens of billions of solar masses scale, even when we argue conservatively. That statement is an order of magnitude answer, not a trophy, and it is meant to survive revisions. It admits that individual objects may move up or down as calibrations improve and as hidden biases are removed. We can also state what we know about physical size with more confidence, because the conversion from mass to horizon scale is straightforward. A tens of billions solar mass horizon corresponds to solar system scales, measured in tens to hundreds of astronomical units. A useful visual is to place the horizon where familiar orbits live, not where science fiction expects a point. Depending on the mass, the radius can rival the orbit of Neptune, and the diameter can approach the scale of the Kuiper Belt. That scale is counterintuitive because the horizon is huge while the average density can be modest. The black hole is not a dense ball, but a vast region where space-time geometry forbids escape. If you could hover far away and watch a probe fall in, the probe would not explode at the horizon. The drama is not at the boundary, but in the fact that signals from inside can never return, no matter how bright the probe tries to shine. We can state what we know about influence with equal clarity, because gravity leaves measurable signatures in motion. These black holes shape stellar motions in galaxy centers, and their gravity helps organize the cores of the most massive galaxies. In a cluster's central galaxy, the black hole sits where the gravitational potential is deepest and most stable. That stability matters, because it makes the nucleus a long-term sink for mass, angular momentum, and eventually other black holes. When active, we can state what we know about energy reach, because jets and winds write on gas at large scales. Jets and winds can heat and displace gas across kiloparsecs to hundreds of kiloparsecs, altering cooling, star formation, and cluster weather. The word weather is not poetic exaggeration, because intracluster gas is dynamic and structured. It sloshes, mixes, and forms turbulence, and feedback can change how quickly it cools and how it circulates through the core. So what enables such growth? And is there one universal pathway that always wins? The evidence argues against a single route, because the three cases live in different eras and different fuel regimes. TON 618 points to early, rare conditions with abundant cold gas and rapid delivery when galaxies were assembling fast. Phoenix points to long-lived reservoirs where feedback and cooling fight over where energy lands, and where the outcome can swing with timing. Holmberg 15A points to long merger histories in deep potentials, where mass can accumulate quietly. In that path, light is not the tracer, and the fossil record is written into cores. Across all three, the common requirements are consistent even when the details differ. The biggest black holes need massive halos, persistent or repeated fuel supply, and enough time for many growth steps. They also need retention, because mergers can kick remnants through gravitational wave recoil. When two black holes merge, asymmetric gravitational wave emission can impart a velocity kick, and shallow potentials may lose the remnant. The deepest cluster potentials help keep the central black hole anchored, allowing growth to continue. In that sense, clusters are not only reservoirs of gas and galaxies, they are cages that prevent the prize from escaping. This resolves the central question in a disciplined way, without pretending the uncertainties are gone. Black holes can get at least to the tens of billions regime, and the universe builds them through rare combinations of environment and history. The payoff is not a single number, but a framework that tells us what we are really measuring. Mass, horizon scale, and influence describe different kinds of bigness, and each is measured by a different observational contract. That contract is always indirect, because black holes do not emit light on their own, and that is the central irony. We infer them from the motion of stars, the behavior of gas, and the way radiation is processed near the edge. In quasars, the light is bright, but the geometry is uncertain, so we trade clarity for reach. In nearby galaxies, the geometry is clearer, but the angular scales are tiny, so we trade reach for resolution. This is why uncertainty is not an embarrassment in this story, but a feature of honest measurement. It is the cost of measuring an object defined by what cannot return, using messengers that can. Now we connect the giants to cosmic history, because that is what they ultimately record in their masses and environments. Each ultramassive black hole is a keystone in structure formation, linking galaxies to their surroundings. Feedback ties the fate of stars and gas to a central darkness, and it does so over long timescales. It can quench star formation, maintain hot atmospheres, and regulate how baryons settle inside dark matter wells. Historically, this idea matured as astronomers realized galaxies and black holes scale together in surprising ways. Correlations like the black hole mass, velocity dispersion relation suggested coevolution, even if the causal arrows are still debated. In the early universe, rapid growth may have helped shape the first massive galaxies, because energy output can alter gas supply. In clusters, long-term heating helps decide whether cores cool into stars or remain suspended as plasma. In the late universe, merger-built relics may mark where hierarchical assembly, concentrated mass over billions of years. Their quietness may be the point, because it hides the final ledger. This brings us to the open mystery, and it is not a small one, because it challenges our census methods. Are there 100 billion solar mass black holes in the quietest cluster cores, invisible because they are not feeding? If they exist, light may not reveal them, and our catalogues will remain incomplete by design. A dormant giant does not advertise itself, and even its sphere of influence can be difficult to resolve at cluster distances. The next census may come from gravitational waves, which can measure mergers without needing luminous accretion. In that channel, the universe speaks through space-time itself, and the signal carries mass and spin in its shape. LISA and future detectors could reveal a population we cannot see with telescopes, especially in the massive merger regime. Waveforms can give masses and spins directly, and they can test whether mergers can build the top end. At the same time, extremely large telescopes will push stellar dynamics to finer scales, making the quiet giants less ambiguous. Better resolution and wider kinematic maps will shrink degeneracies, turning plausible giants into measured ones. X-ray observatories will refine the feedback accounting in cluster cores, where the energy bookkeeping is currently approximate. They will measure turbulence and shocks more directly, tightening the link between black hole work and intra-cluster thermodynamics. As these tools arrive, some famous masses may shift, and some famous candidates may fall. The point is not to defend a record holder, but to map the corridor of plausible growth histories. We end where we began, with darkness as evidence, because the theme is methodological as much as it is cosmic. The largest black holes are not defined by what we can see, but by what they control. They are not merely endpoints of collapse, but ongoing experiments in gravity, time, and cosmic evolution. Their horizons mark a boundary, clean, mathematical, absolute, yet their influence extends through galaxies and clusters. Somewhere in the deep past, something grew vast enough to swallow solar system scales in shadow. The deeper truth is that it also swallowed time, storing a history we are still learning to read. The final answer is therefore both measured and unfinished, which is the honest shape of the science. The universe can build black holes of tens of billions of suns, and it may hide even larger ones in the quietest places. We do not solve the darkness by looking for a face, because there is none to see. We solve it by tracing the motions, the heat, and the missing light that orbit around an absence. And when we ask how big the largest black holes are, we are also asking what the universe had to become to make them. The record is still there, waiting in the deepest wells. Across this journey we learned that big is not one number. It is mass, horizon scale, sphere of influence, and energetic reach. We watch those definitions collide with reality, where spin reshapes the innermost orbits, feedback throttles the fuel line, and even density can fall below water as giants grow. And we met three different witnesses to cosmic construction. Ton 6-18 in the early glare of quasar light, Phoenix A in a living battle between cooling gas and jet heating, and Holmberg 15A in the quiet archaeological record of scoured stars and ancient mergers. Ton 6-18 reminded us that the farthest monsters are measured through a ladder of inference, built from broad lines, luminosities, and calibrations that can tilt with orientation, winds, and hidden lensing. Even if its mass is inflated by systematics, it still sits uncomfortably close to the edge of what steady Eddington growth allows in a young universe. That tension forces the same hard choices again and again. Bigger seeds, longer duty cycles, brief super Eddington phases, or merger-driven leaps that must somehow dodge feedback self-sabotage. Phoenix A shifted the story from distant light to nearby environment, letting us map the supply chain directly in X-rays, radio, and filaments of cooling gas. There, the question is not whether a black hole can heat its surroundings, but whether it can heat the right place at the right time before precipitation turns into starburst fuel. Phoenix's extreme cool core may be a rare flare in a thermostat that usually works, or it may be evidence that geometry and delay can make feedback miss the wound, leaving the inner core to keep bleeding heat. Holmberg 15A, by contrast, spoke in silence, showing how the biggest black holes may hide where the universe's oldest and richest in mergers. Its depleted core hints at past black hole binaries ejecting stars like debris from a gravitational slingshot, yet its true central mass remains entangled with modelling degeneracies, resolution limits, and assumptions about dark matter and stellar orbits. Together, these systems expose the deeper pattern that the practical ceiling on black hole mass is set less by theory than by delivery, by how galaxies funnel gas, how clusters store it, and how feedback negotiates with gravity over billions of years. In the end, our record holders are also our measurement limits, and the biggest uncertainty may not be any single object, but the census itself. If ultramassive black holes spend most of cosmic time dormant, then catalogues built from bright accretion could be missing the true top end entirely. The next chapter of this story belongs to sharper tools, extremely large telescopes resolving spheres of influence, next-generation X-ray observatories tracing where jet energy really lands, and gravitational wave missions like LISA, listening for the mergers that build giants when light is absent. So how big can a black hole truly get? And what do these three giants reveal about the universe's largest structures? The answer is that there may be no clean upper wall, only a moving frontier set by time, fuel, and feedback. And the biggest black holes are defined less by what they are than by what they can control. TON 618, Phoenix A, and Holmberg 15A do not just compete for a title, they sketch a single cosmic biography. Growth in the early blaze, regulation in the hot cluster storm, and quiet accumulation through mergers when the lights go out. In that sense, the darkest objects become the clearest records, because every extrasolar mass is a fossil of environment, gravity and time, written where we cannot look directly. When the next observatories sharpen the ladder of inference and gravitational waves reveal the mergers behind the silence, watch how the record books change. Because the universe may still be hiding its largest builders in plain darkness,